Pavel?
Yes.
When somebody asks a question by raising the hand, and then you know I mean, how do they do I have to do something like to lower the hand again, or?
Well, in principle, yes. Otherwise, you'll get confused if they want to ask again or not. Okay. Well, there will be options like in the participant list that you can lower their hand. Well, at least this is what I did. I mean, otherwise you can get confused like, as I want to ask again or not. And I think it's like if several people raise a hand, it's ordered by the I mean by who did it first. So it's automatically ordered.
So should we start, Pavel?
Yeah.
Okay, so hello everyone, and welcome to the third day of the school. Today we're starting with the first lecture of Pavel Putrov, which is a continuation of the previous lectures by Atish on 3 avatars of mock modularity. Please, Pavel.
Thank you. So I will start by reviewing some basic facts about so-called six-dimensional n equals 2,0 series, which I will need later to make some connection with what Atish told us about. And so first, yeah, the kind of one has to keep in mind the following important fact about classification of this series with n equals 2,0 supersymmetry. The fact is that the six-dimensional 2,0 superconformal field series are classified by Lie algebras of the following form. So the Lie algebras such that they can be decomposed into direct sum of some simple components gi, where each gi is either just a U1 or of ADE type, or equivalently simply laced Lie algebra. Okay, so I'm not gonna, and we are not gonna need kind of to use the full structure of n equals 2,0 supersymmetry in 6 dimension. But what will be important for us is the following fact, that this n equals 2,0 6D Euclidean. So I will always in my talk, I will assume that space-time is Euclidean supersymmetry. Well, let me talk about group, supersymmetry group, which is the extension of a group of Euclidean isometries in 6 dimension. It contains, in particular, the following even subgroup, or if you wish, bosonic subgroup. Spin 6 times spin 5 R. So what is the meaning of these two factors is the following. So the spin 6 is a spin, meaning a two-dimensional cover of SO6, a subgroup of rotations in a 6-dimensional space. And spin 5 R is what is known as R symmetry. And it has, so the supersymmetry algebra has 16 supercharges transforming in a representation 4 plus, 4 of this symmetry, spin 6 times spin 5 symmetry. So 4 plus is a chiral chiral spinor representation of in 6 dimension, and 4 is a spinor representation of spin 5, where there is no distinguishment between chiralities. So let me actually remind you some basic facts about spin groups. So first, I mean, one way to define the spin group is that, as usual, it's a double cover of usual SON group, which you are all familiar with, or equivalently, it fits in the following short exact sequence of the group. And it's also important to know that in low dimensions there is the following groups isomorphic. So spin 3 group is isomorphic to SU2, and spin 4 group is isomorphic to SU2 times SU2, and it will continue to distinguish these two factors by L and R, since they have a meaning of chiral subgroups of kind of chiral rotations of the 4-dimensional rotations. And spin 6 is isomorphic to SU4. And also let me make the following remark. So I talk about the 6-dimensional series can be completely classified by choice of Lie algebra, and there is a particular situation when G is UN or SUN algebra, and then the 6D theory can be understood as world volume theory on a stack of n and 5 branes in 11-dimensional M theory. And in particular, in this, so in the case of UN, it's just a world volume theory of a stack of n brane, and if you want to consider SUN, this just means that we want to fix or remove center of mass degrees of freedom. And in particular, in this point of view, spin 5R can be understood as rotations, a group of rotations of 5 normal directions. So we have spin 6 rotates along the 5 brane, rotation along the 5 brane, and spin 5 are rotations in the orthogonal direction. And the other important fact which will be relevant for us, and I want to remind you, is that the 6D theory, if you take this 6-dimensional theory, suppose it's labeled by a certain Lie algebra G, and consider its compactification on a 2-dimensional torus, which can be understood as a quotient of C divided by Z plus tau Z. So it's a 2-dimensional torus with equipped with complex structure tau. So we get some effective 4-dimensional theory, and this 4-dimensional theory can be described by a 4-dimensional n equals 4 super Mills theory with gauge group G, such that the Lie algebra of this group is our small g, and complex coupling tau, which is a composition of the usual real-valued gauge coupling and theta, which is a theta angle. So in particular, the 4-dimensional action has the following form. It has, for example, the term 1 over g squared trace f wedge star f, where f is a gauge field, and also have a term e theta divided by 2 pi integral of trace of just f wedge f, so the standard theta term. And so here you can see there's some kind of finite ambiguity, because there can be different choices of a Lie group which has the same Lie algebra. And so this choice, I'm not going to talk about much about it, but so this choice can be understood. So it's related to the fact that 6D theory is what is called relative theory, and kind of this additional extra choice, which is just a kind of finite choice of data, is similar in a sense of the choice of when you do the choice of a conformal block, when you consider chiral 2-dimensional theory. So in many senses, it's similar to this. But so in particular, well, what will be important for us if, for example, if G is if you have SUN Lie algebra, there are two, in a sense, canonical choices. One can take, for example, G to be equal to SUN, or G to be equal PSUN, which is SUN quotient by the center. But these choices are actually closely related to each other, and as we will probably encounter in the lecture by Clay corridor next week, one can actually go from one to another by gauging certain one-form ZN global symmetry. Okay, maybe if there are some questions.
I do not see. Oh, there is one question from Will Silva. What about the tower of KK modes in the reduction to 4 dimensions?
Yes, it's a good question. So in general, well, there is kind of folklore, kind of belief is that you actually include all tower of KK modes if you count all instantons properly in your 4-dimensional theory. And there's like in the case when the group is SUN, there's more or less no ambiguity of counting instantons. But when the group is something like U1 or UN, there is some kind of ambiguity of what you really understand by instantons. But if you because I mean, roughly speaking, you have to include point like instantons to recover all KK modes. which might be not completely obvious from. It's kind of obvious, it becomes obvious if you consider embedded into a string or M series, but from the point of view of just four-dimensional series, it's not completely obvious that you need to include this point like this.
So there's a follow-up question. Is there a mass scale?
No, here there is no, all parameters are dimensionless. Just tau, it's a dimensionless parameter.
I think you can go on, Pavel.
Okay. So the next thing I want to review is what is called notion of a topological twist. So we want to consider, in particular, the theory on the space-time of the following form: M4, some four manifold times sigma 2, some two-dimensional surface, and very kind of informally, the procedure of topological twisting can be formulated as follows. So you want to identify the spin 3 subgroup of spin 5R symmetry. And this spin 3 subgroup is just a subgroup of rotation of 3 out of 5 directions with another kind of copy of spin 3, which we can find inside the symmetry of the space-time. Namely, this spin 3 is SU2 left inside spin 4. So this is one of the SU2 factors in spin 4 factorization into SU2 times SU2. And this, in turn, this spin 4 is just a subgroup of spin 6, which you had before. This is a subgroup of rotations along our four manifold, M4. So practically what this means that when we put a theory on a curved four manifold, we turn on background spin 3, which is a subgroup inside the spin 5, a global symmetry, gauge field equal to SU2 left component of spin connection on M4. So we kind of get some locking between the R symmetry, the global R symmetry, and the symmetry of our spacetime. Okay. And okay, let me make the following remark. When so the sigma 2 is T2. So as I mentioned before, if you compactify on T2, then you get some effective four-dimensional theory, and this twist from the point of view of the four-dimensional theory is known as Wafo-Witten twist of n equals 4 superyoung Mills. So when sigma equals 2, this is equivalent to Wafo-Witten, or we'll use this abbreviation, BW, Wafo-Witten twist of n equals 4 for the superyoung Mills. I mean, this is more or less identical equivalence. So we can just use the definition that we have instead. And okay, and for our purposes, we also need to do the following kind of exercise. Well, I'm not going to do this, but yeah, I leave this in the exercise, and in the notes you can find kind of more detailed description of it. So what happens when we consider, so our six-dimensional fields, which reduce to certain four-dimensional fields, they transform in some representation of spin 6 times spin 5. But once we do this topological twist, they kind of representations effectively are going to get modified. So what this means in particular is that, so if you consider the following representations of spin 6e times spin 5r, after the twist, decompose as follows into representations of spin 4 times spin 2, where, well, spin 4 is a again, it's first of all, it's isomorphic to SU2L times SU2R. So I used a small r here. And so this is the rotations on along M4, and this is the rotations along sigma 2. And this spin 2 is, of course, just isomorphic to U1. Okay, and for our purposes, we need to consider the following representation. First, we want to consider representation 4 plus, comma 4. So the same representation as a supercharger's head. So again, it's 4 plus is a representation of spin 6, and 4 is a representation, 4-dimensional representation of spin 5. And the statement that it decomposes as follows: it's 2 copies of representation, which I will denote by 1, comma 1 with index plus 1/2. So what this notation means is that, so this is a dimension, the first number denotes the dimension of respect to SU2 left, the second number denotes the representation with respect to SU2 right, and this is denotes spin or charge of spin 2, the spin 2. And by following this notation, there also will be 2 copies of representation 3, comma 1 with 2-dimensional spin being plus half, and 2 copies of representation 2, comma 2 with 2-dimensional spin being minus 1/2. And so in particular, you see this is so these guys, they are just scalars on M4 because they transform into as a trivial representation. And these guys, so they transform as a 3, comma 1 representation of spin 4. And it's easy to see that this is a representation which self-dual 2 forms on M4 transform as. And 2, comma 2 is are just vectors. And we also want to consider representation 1, comma 5, and decompose it as follows: 2 copies of representation 1, comma 1 with 2-dimensional spin 0, and 1 copy as representation 3, comma 1 with 2-dimensional spin being 0. So this is, in principle, this is just exercise in the representation theory, and I will leave it to you.
Pavel, there is a question by Yun Bao Wu. Is the topological twist trivial for the case when sigma 2 is equal to T2 with flat metric?
Well, the topological twist is actually here, it's independent of what is going on sigma 2. So because we only, in this description of the twist, we only kind of engage the spin 4 subgroup of spin 6, which is correspond to rotations of 4 or rotations along local rotation along the 4 manifold. So we don't really do here the spin the twisting along sigma 2 at least in this setup. I mean, one can also do the twisting along the sigma 2, but we don't do this. So at this point, it doesn't matter what is is sigma 2 curved or not.
Sorry, Pavel, and I also have a question. Could you maybe quickly remind us? I guess you can also get the other twists of the n equals 4.
Yes.
Could you remind us why we focus on the Vafa-Witten twist specifically?
Well, it's yeah. So so this is a one can answer that that we want to do this. It's just our choice. But indeed, in principle, so the other twist, and they would go something like this. So in particular, instead of doing this, we could pick some other subgroup, some other spin 3 subgroup inside spin 5, embedded in some other way. So here we just take spin 3, embedded by just restricting the rotation to 3 out of 5. But there are other inequivalent ways to embed spin 3 into spin 5. And this would give us another topological twist. And there are also even more different way is that one can take just a spin 4 subgroup in spin 5 instead of spin 3. The subgroup of rotation of 4 out of 5 direction. And identify with the whole, not just with the chiral part, but identify with the whole spin 4. And would give us actually third twist. So overall, there are actually 3 inequivalent twists. But yes, the twist which we do, which is called Vafa-Witten twist, it's a topological twist, and it's good for some reasons which I actually will mention a little bit later. But well, briefly, we can say that this is a twist when the partition function actually, in particular, is generically non-vanishing.
Okay, thanks.
And so from this result, we can see, so there, this part, we can see that when we do the twist, after the twist, we get always get two scalar charges on a full manifold. And this means that in particular, there are always at least 2 unbroken supercharges, which are scalars on a full manifold. And we also see from this representation theory exercise that they both transform as right moving spinors on sigma. So if we didn't do a twist, we would have to look for some sort of covariantly constant spinors to find unbroken supersymmetry, but in general they would be absent. But after the twist, because since they are always the scalars, always covariantly constant scalars, we always have at least 2 supercharges. But in principle, there can be more, depending on the holonomy of a full manifold. Okay, and so then we want to consider the following quantity z, which I will know z with index g, depends on the choice of full manifold, and tau will be the partition function of the 6D theory on M4 times C2. So now I'm taking sigma 2 to be 2 torus. And using this correspondence, which we discussed, this is also equal to the partition function of Vafa-Witten theory. So in principle, one would be able to consider just work in 4 dimensions and consider this Vafa-Witten theory and topological twist completely inside 4 dimensions. But I'm using this approaching this using this higher 6-dimensional perspective because we want to connect to something like elliptic genus later, which is what was mentioned by Atish in his lectures. And this partition function, it has the following expected quantities. So first, yeah, this quantity, which is kind of looks weird, but it's actually not, with this property. Sorry, what? Not quantities. I wanted to say properties. So the first property may look weird, but the partition function is non-zero, meaning generic non-zero. But this is actually non-trivial because in many cases, once you do a topological twist, the partition function itself actually vanishes due to what is called ghost anomaly. And one has to get something non-trivial, one has to consider correlators, not the partition functions. But here, and this is what is good about Wafo-Wheaton topological twist, the partition function itself is generically non-trivial. And the second property, which will be kind of the most important for us, is can be called S-duality, where here G hat is a Langlands dual, what is called Langlands dual of G. So we'll be interested in the case, in particular, when G is, for example, SU2 and G hat is PSU2 or equivalently SO3. So the statement that if we change if you change coupling constant tau to -1 over tau in the n equals 4 superreals, the theory is equivalent to more or less itself. Well, it has just with correction that the global group structure may become different as it happens here. So SO3 and SO2, they have the same Lie algebra, but they have a different global group structure.
Pavel?
Yes.
So the transformation of tau in this equation is intuitively sort of clear from the geometric point of view of the reduction of the six-dimensional theory. Is there an easy way to see how the Gauge group transforms? Why we interchange G with G, the Langlands dual?
It's possible, but it's not very easy.
Okay, thanks.
You mean the question why it's so naively? Yes, naively from. Well, let me comment a bit about it. So naively from. If everything was kind of nice and usual in a sense, so naively, when we reduce a theory to if we compactify first on the formal, we get some two-dimensional theory. And there you would expect from partition function just, if it's conformal theory, to go, if you change tau to -1 tau, it just goes to itself. But this doesn't happen because the 6D theory is what is called relative theory. And this, in particular, this implies that the two-dimensional theory becomes also what is called relative theory. So as a simple example of relative theory, you can think about in two dimensions. You can think about, for example, chiral with the Wheaton theory. So it doesn't have any, in particular, doesn't have a fixed partition function, but it has a vector of partition function. In other words, you have to choose a conformal block on a torus. And when you do S transformations, then these conformal blocks, they transform into each other. They don't transform to themselves. So this is a brief explanation, but one can actually figure all the details and see why actually G goes to G hat.
Thanks.
Okay, the third expected property is that the anti-holomorphic derivative with respect to tau of this partition function is 0. This is kind of naive property, and so as you can expect, this is actually what will fail for us in certain cases. So what is the naive argument why this happens? So naive argument goes as follows. So the four-dimensional, just on a classical level, one can show that the four-dimensional action has the following form. So one gets separated term tau times trace FHF, and the rest can be represented in this form, Q of something, where Q is one of the unbroken supercharges. And then, if we if we act of this anti-holomorphic derivative on our path integral, which can be written as follows schematically. So phi here is a collection of all fields. And so we also use the fact that, of course, Q is symmetry of the series. So this is the action itself is killed by Q. And then one can easily see that this can be rewritten in this form: d of phi, integral of d of phi of Q of something. This is because this part, which is not Q of something, which is not Q exact, is holomorphic in tau, and all anti-holomorphic dependence on tau can be considered here. And then, well, we know that this is a Q can be understood as a derivation on the space of fields. And because in particular, if you choose some sort of coordinates on your space of fields, you can always, in particular, write any generator of any symmetry in this form where alpha I is a result of acting by the generator on the coordinate phi I. So it's a derivation, and by using the Stokes theorem or equivalently integrated by farce, one can argue that this is zero if no contribution from infinity. And usually this is indeed what happens, but in some particular cases, as we will see, this is actually not true, and one can get some contribution from infinity, and we will calculate what is it.
So there is a question by Thomas Codina. Do you have any T-duality relation for the partition function?
Yes. Okay, let me say the following. So this, for SU2, the partition function is invariant under T-duality. And for SO3, if you act by T-duality, it kind of gives, well, roughly speaking, it gives the same. It also gives you SO3, but with certain kind of background one-form symmetry turned on. Well, it may be more a bit later. It will be more clear actually what how the T-duality acts. But again, let me say the one. If one can, for SO3 partition function, one can split it into kind of sectors different by the discrete magnetic charge. If one splits this into such sectors, then the T-duality will act just diagonally by some phases. Okay, and another property, which is also a nice property, is that the derivative of this partition function with respect to metric on a four manifold is also zero. So the argument is really the same as here before, because you see what was important actually here was that this part doesn't depend on tau bar, but we also see that this part also doesn't depend on a metric. So one can make the same argument for this. But this also can fail if there is some contribution from infinity. But in a good situation, this partition function is supposed to be some topological invariant, since it doesn't depend on metric. And moreover, under certain circumstances, well, there's some technical assumptions on kind of positivity of curvature, but let me don't go into detail. there is a kind of a more geometric interpretation of this partition function, which is a topological invariant. Sorry, this is not. So under such assumption, one can show that this is the partition function can be computed using localization, and the result is the following series in Q. So Q, we always use the following convention. The Q is exponential of 2 pi times tau. And so the coefficient in terms of Qn is chi of moduli space of n g instantons on M4. So chi here is Euler number. And well, this is, I can remind you, this is solutions, the spatial solutions of anti-self-duality equation on the gauge field with fixed integral of trace f which f, and we have the quotient modular gauge transformations. And in nice situations, this becomes a finite dimensional, actually smooth manifold, and we can calculate Euler characteristic. But this is not always the case, and then can actually modify a bit this result. So let me don't go into details. But what, in principle, suppose we kind of be naive, and let us just try to define kind of naive partition function just by this formula. Suppose we can calculate the right-hand side and see what happens if we just use this as a kind of naive definition of partition function instead of full-fledged path integral. And let's see what happens for M4, which is CP2. And what happens in particular when the partition function is for SU2, this can be written as, well, let me write in terms of these functions f0 of tau, and I will tell you what they are. And for SO3, the naive partition function would be f0 of tau plus f1 of tau. And where fv, v is 0, 1, I define them as the following series, which you, well, up to some simple power of eta function. You already seen this series in the Atish lectures. Where okay, eta is a eta function, and h is what is called Hurwitz class numbers, which were already mentioned by Atish. So this is just some numbers. And so what what happens if we try to plug in this naive partition function, this kind of expected inequality? So is it, we can ask, does it hold or not? And well, no, it doesn't hold, but it's almost true. This equality almost holds. And what almost means was explained by Tish. So this means that the what exactly this means that these functions fv of tau, which appeared, they are can be thought as components of a vector valued mock modular form, and it has a non-holomorphic completion by adding to this fv function g, which depends both on tau and tau bar analytically. And if you take formally tau bar to infinity, it goes away, this gv. And we also know what is this, if you use this particular, if you use this non-holomorphic but modular completion, non-holomorphic but modular. So we know for this, what is the anti-holomorphic derivative of these additions. I remind you that tau2 is the imaginary part of tau, 16yi. So this is, again, something which has already appeared in the Atish talks. And so this gives us prediction. If we assume that this is, so we expect the partition function to be actually modular, we expect modular properties to be more important. And we can expect that this non-holomorphic but modular completion, we can expect that this gives us actually this full physical partition function. And if we assume that this is true, this gives us also prediction for the derivative of the partition function with respect to tau, just by plugging these additions into this relation, by completing this right-hand side of this of these equalities. But we want, our goal is want to derive this directly. Any questions?
I do not see any questions at the moment.
Okay. Then I can continue a bit. And what we will do is, so we'll do it by what can be called reversing order of compactification, which we already talked a little bit about. So order of computation of 6D series on M4 times T2. So before we consider it, we compactify on T2 and we get some n equals 4 four-dimensional angles, which we topologically twisted. But suppose we first compactify on M4, so then we get some two-dimensional series, which is usually people denote by TG of M4. This is effective 2D series on T2. Again,
sorry, Pavel, I'm sorry. Can I ask a question?
Yes.
As a matter of principle, could we study this question directly in the four-dimensional theory without using this six-dimensional construction and the reduction on T2?
Yes, absolutely. And yeah, if you look, in our recent work with Atish and Edward Wheaton, we actually do this also directly in 4D without it. But okay, actually, in using this reverse order of creation is actually easy in a sense to derive this. Mm-hmm. But in many senses, it's kind of derivation is analogous. And I also, yeah, so yeah. Mostly because of the time constraint, I don't have time to talk about two different approaches, and I will focus on this kind of two-dimensional perspective. But
sorry, there's one more question in the chat by Eres Urbach. So, what is the correct expression for Z as opposed to the naive one? So the question, I guess, for this in this particular case of CP2 is essentially well, this kind of
yeah, again, the prediction from modularized correct expression would be given by changing FV to this FV plus GV. This would give a correct expression. But here we are not going to derive full Z. What we are going to derive is the derivative with respect to tau bar. But in principle, if one knows what is a holomorphic anomaly by kind of making some other additional kind of assumptions, one can recover. If one makes some additional term, one can uniquely recover the full Z, not just derivative with respect to tau bar. But I'm not going to talk about it. Any other questions?
No, I think you can go on.
Okay, so okay, let me go for some time and then I will stop. So yes, and then from this point of view, so before we considered this partition function, which is denoted by ZG and 4 tau, and it was given by the. So, but if you reverse the order complication, this can be also the partition function of this effective two-dimensional theory, and it has therefore the following form, where well, H is a Hilbert space of this two-dimensional theory on S1 on a circle, and as usual we denote L0 and L0 bar. They are combinations of Hamiltonian and momentum along this space circle, which we're considering. And again, from this exercise before, from the exercise, we saw that this TG of M4 has at least two moving supercharges. And each of these supercharges, when squared, is equal to L0 bar, the kind of the right moving momentum. And if one applies this argument, naive Witten's argument, which Atish mentioned, naively only states with L0 bar equals 0 contribute in the trace above because of the cancellation between Bosonic and Fermionic modes. Sorry, because of cancellation, yeah, but Fermionic and Bosonic non-zero eigenstates, and this gives us the other argument that kind of the other naive argument that this should depend only on tau, but not a tau bar.
Pavel,
yes,
Ali Shepherd is asking, what is the argument for this equality between Vafa-Witten partition function and 2D partition function?
Okay. So first of all, we can use two facts. The series is conformal, and so we can kind of shrink simultaneously. In particular, we can shrink simultaneously T2 and M4. And the second fact is that we used a topological twist. So at least so the theory doesn't depend in particular metric on a four manifold, and you can shrink the size. So we're interested in kind of topological invariant of four manifold, and then we can also shrink. We can change the size of four manifold independently of the size of two-dimensional surface. And this combination of these two facts tells us we can shrink them independently, kind of shrink or expand independently, and the result is not going to depend. so we can reverse the order of computation. So roughly the argument like this. Any questions?
No, there are no more. Yeah, wait 1 second. But as the 4D theory kept all KK modes, does the 2D theory also have all KK modes?
Yes, 4D series has all KK modes, yes. Well, I mean, we're interested in only, well, to be precise, let me say that let us consider only quantities which are kind of, yeah, we can consider quantities, observables, like partition function, which are protected by this supercharge, by the unbroken superset.
So one more question. What are the boundary conditions for the fermions, especially along the T2?
Yeah, the boundary conditions are periodic along both circles. In particular, well, I mean, yeah, so here S1, we're considering these periodic boundary conditions on fermions, and this insertion of minus F tells us that along the time circle, they also have periodic boundary conditions. But this is what we need if you want to preserve supersymmetry by default. We compactify on circles with periodic boundary conditions on fermions. Anything else?
There is one more question by Muhammad Numan. What about the partition function Z of G as the generating function of the elliptic genera? How does the mock modularity appear in that case?
Well, maybe I'm not quite understanding the question, but well, the statement. So, okay, first, the statement is the partition function is equal to this trace, which can be called elliptic genus of the effective two-dimensional series. And in both cases, yeah, the mock modularity appears because so from this four-dimensional point of view, the mock modularity can appear, well, as I sketched, because of some contribution from the boundary in this class integral. And from the point of two-dimensional theory, yes, the mock modularity will appear from some sort of, as I just explained, with equivalent things, which kind of related things, which are non-compact kind of continuums of the spectrum, or non-compactness of your theory, if your theory happens to have some sort of signal model description, some target, which will be indeed the case. So effectively, one will be able to describe this two-dimensional theory as some sort of sigma model with non-compact target, and we will see that mock modularity will appear from this non-compactness of the target.
So one more question related to the previous one by Ohad Mamrud. Is it also true for any circles that might exist in M4, meaning that the fermions have periodic boundary conditions?
Okay, yeah, that's a good question. So in principle, we would have to choose what is the kind of boundary conditions on fermions along M4, like along circles, which is equivalent of what is called choosing spin structure on M4. In principle, one has to do this, but what happens in after this Waffer-Witten topological twist? Actually, all fields, then we are not going to have any spinor fields after the twist. So you can see in particular in this, as a result of this exercise, so here we started with some spinor, some fields which were spinors in principle, but after the twist, everything, there are no spinors in the right-hand side. Everything, you don't need to choose a spin structure for manifold to define it. But for some other twists, you actually would need to also specify spin structure for manifold.
So Pavel, there are a few more questions, but do you want to finish your lecture first, and we take them afterwards?
Well, I think it's maybe then I should just stop here then. And,
okay, then let's unmute and thank Pavel. And if you have questions, raise your hand or write a question in the chat. So let me read you a couple of questions. Ritam Sina is asking, why do you compare the 4D partition function to the index of the 2D theory as opposed to its partition function?
Yes, thanks. So this is related to the previous question. So for the partition function, well, what it usually means is that we don't, I guess, we don't insert this minus 1 to the f, and this would be meaning that we choose anti-periodic boundary condition on the time circle for Fermat's. But we need to use, for both circles, both special circle and the time circle, we need to use periodic boundary condition, because this is a, well, you can understand this is in the statement which I made before, that if it takes 6D series and compactify on a torus, we get some 4D superring mills in 4 dimension. So this statement assumes that we choose periodic boundary condition on the torus. So this is a kind of, this is part of this built-in this correspondence between 6D series and 4D superring mills. So that's why we end up with the index, not the partition function.
There's another question by Yun Bao. In what sense do we discuss T-duality of the 6D theory, since it is not a sigma model, so it does not have target space? Would you like to repeat the results about the T-duality?
Okay. Well, I think what so S. Okay. So S duality was related to this change of coupling constant, but T duality, at least, well, what I thought was, for example, previous question about it was considering this change, this type of change of coupling constant. So essentially, it's equivalent, as you can see from the definition of tau. Well, it's something like 4 pi I g squared plus c to 2 pi. This is equivalent to shift of theta angle by 2 pi. And for SU2 Young-Mills series, it's a symmetry, just the fact that it depends on theta angles less periodic. And for SU3, it's a bit more subtle. That well, because it's symmetry when you change it by, well, in this normalization, it's a symmetry when you change it by 4 pi, but if you change it by 2 pi, it's kind of, well, it gives you essentially the same theory, but with some sort of background one form.
So Kai Sun is asking, what about the compactification of 6D 1,1 gauge theories? Anything interesting there?
6D 1,1. Well, there are definitely interesting things for 0,1. So I guess it implies that there are interesting things for 1,1. So, but I haven't considered 1,1. Well, okay, for 1,1, you might get into trouble that after you compactify, like if you take, for example, 0,1 6D series, then in general you get in 2 dimensions. You can make a twist, and in that case, actually, is a unique twist. Then you get 0,1 two-dimensional series, and you see it's still defined index. And for index, it's enough to define an index like elliptic genus of 2-dimensional series. It's enough just to have a single right moment supercharge. And there you can, you can get some other invariants of like 4 manifolds, and they related to this to the indices of this two-dimensional thing. But for 1,1, I haven't really thought about it. But I think one might end up in trouble that you get some sort of, well, it might be not a trouble, but some confusion. You get a 1,1 two-dimensional series, and then well, for 1,1, the elliptic genus, it's not going to depend, because you have both left and right moment symmetry. It's not going to depend both on tau and tau bar, at least if you just calculate this. I mean, still consider periodic bounding. But yeah, I mean, it's something I guess one can consider, but I haven't thought about it. But maybe it makes sense in this case to consider some sort of break partly supersymmetry.
Mm-hmm. So Yvonne Zavala has raised her hand. Maybe Yvonne, you can ask the question.
Yeah, thanks. Thanks, very nice lecture. So when you wrote down your naive partition function, you said under certain assumptions. So what are these assumptions, and could you have arrived to the correct one, or what? I mean, I want to know a bit more how you get there.
Okay, the naive assumption, well, it's hard to formulate kind of necessary and sufficient conditions, but let me write you a certain sufficient condition. Sufficient conditions, for example, M4 is scalar, and there are some what is called first chunk loss of this M4 is I think non-negative. Then what is what is called you have what is called vanishing theorem, and then you can show that everything localizes on these solutions of instanton. More generally, one can argue that it localizes on what is called solutions of Wapf-Witten equations. And then you would get, you can define these invariants using so-called virtual error numbers. But it becomes a bit technical.
Right. So basically, this naive expression will satisfy that the derivative, of course, with respect to tau bar is 0.
Yeah, because by definition, it's just homomorphic function in Q and in tau.
Right. So just a second question. So now, since it was mentioned, a posteriori, since you said you can get the results without going through 6D, so just from 4D point of view,
yes.
Is there anything extra you learn from the 6D sort of route, way to do it?
Okay, the 6D, one thing which is actually, you cannot quite, well, at least we couldn't do this in 4D, but you can do using the 6D perspective, it's fixing the overall numerical coefficient of the result. In 4D, yes, it's subtle and we couldn't really do this. But from 6D point of view, you can fix it. And one can see that, for example, from the way that in 4D, when you consider partition function of 4-dimensional theory, it's hard to define kind of overall normalization, how to fix the overall normalization. But if you consider something of the partition function of something on the form circle times something, then you can always interpret it as a trace of the Hilbert space. And the trace, the partition function is interpreted as a trace over some Hilbert space, and it has a canonical normalization, which is easy to fix. So so one thing is actually you gain by using the 6D. One concrete thing is fixing the overall kind of numerical number.
Okay.
Okay, so there are a couple more questions, but I think we're running a little bit late. We need to take a break for the next lecture. So please, you can ask your questions during the tutorial later today or tomorrow during the lecture. So let's thank Pavel again. And now we have a 10-minute break, and we continue with Ahmed's lecture.
Hi, Kyriakos. Hi, Pavel. Nice, very nice lectures.
So we're being live streamed right now, or is it private?
Yeah, we're being live streamed.
Live streamed, okay.
Yeah, maybe we can discuss organizational matters after this After Ahmed's lecture?
You mean here in this, but sorry, no.
We can discuss it. We can leave this and go discuss it by Skype maybe.
Sure, okay.
So it is, you mean about the questions and how to...
No, also about this, some kind of a social interaction. I was thinking, you know. No, like I was saying to Pavel, you know, that maybe it might not be a bad idea if everybody can introduce, you know, in 1 minute, in 45 minutes, everybody says what they are, you know, where they are from, what they work on, etc. If you can allocate 1 hour for this, you know, and also I think it might not be a bad idea if at the end of the lectures people show themselves, you know. By the way, Nadia, we should take a photo, conference shot. We should take a conference shot with everybody showing their face.
Sure, not mine though. Look at me.
No, that's what I'm saying. We should warn people that, okay, every day after the 3 o'clock lecture, we will say hello to each other. Please come dressed properly or something like that. With your makeup on, yes, right. Yeah, we can think something like that. I was wondering. I mean, I don't know how to do it.
We can schedule this, and I can just screenshot the.
Yeah, first of all, we should take a screenshot of in a lecture, maybe today or tomorrow.
Yes.
And then I think in general, it might be a good idea if people see each other a little bit, maybe after every lecture at 3 o'clock, you know, they see each other. And before they do this social Slack, maybe it would be good if everybody introduces themselves and say that, okay, I'm from here and I'm interested in this kind of things in physics. It might be useful. Otherwise, somehow the participants are not participating really, you know, they are just, we should find some way so that, I don't know, those of you who are hearing, maybe you can show your video.
We can set a time where everyone has to open their video and then.
Yeah. Why don't we do that?
Yeah.
It would be nice to see who are the people attending, no? Also for the speaker. Human Nishad said it's a good idea. Okay, then why don't you show yourself? Okay, there you are. Hi.
Oh, you see now.
Yeah, please show yourself, all of you who are here listening. Hi. Yeah, we have quite a good selection from all over the world. So, yeah, so do you think, Nadia, we can schedule some kind of an introduction meeting?
Yeah.
Without making it too.
So we'll need a little bit more than 1 hour at least or so, right?
Yeah, if you do all 90 together, then we'll need more than 1 hour. We could do it in 2 rooms. I mean, that's not ideal, but we can do it twice.
Uman is saying he can't turn on his video.
Who?
Uman's saying that he can't turn on.
Uman cannot. I see. Okay. Hi, Ahmed. This. Okay.
Hi, Ahmed. Nice lectures.
Yeah, nice lectures, by the way. Yes.
Thanks.
Yeah, maybe.
Yes, I think if you do some introductions and then also people come to know what are the kind of interests of each other, then maybe they can form some social Slack more effectively. And
yeah, maybe not everyone together. Maybe do lots of slots where people can introduce themselves, because otherwise you're sitting there.
Maybe that's a good idea. What we could do is that over the period of next 2-3 days,
even in the breaks, maybe.
Yeah, I think or after a lecture, right? 20 people introduce themselves. Then in 5 slots, we will introduce each other completely. And then we can have one maybe social kind of. Okay, let's think about it offline. Little bit. I will come back in a minute. I'll have coffee.
Hi, Victor.
Hi.
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 So Ahmed, are you going to share your screen?
Yes, yes. Let me do that.
Okay. Great. I have to say that for me, it is a little bit difficult to read the text this time. Maybe the other people can give some feedback.
Okay, let me see what I can do. I can zoom in well, how difficult is it? Like, is it
Maybe
is
you
bottom left?
can zoom.
Yeah, I think it's borderline.
Okay, I think this is well.
I can more or less read it, but it's could be bigger.
See. Maybe I can zoom in when I talk about this point.
Yeah, this is better, certainly.
Yeah, I'll zoom in when I discuss it.
So can we start, Ahmed?
Yeah, whenever.
Okay, great. So we continue now. We're very happy to have Ahmed, who will be continuing with his third lecture on quantum black holes.
Okay, thanks, Kyriakos. So let me begin by recapping our failures from last time. So we had this analysis where we studied, or we computed the entropy of the Hawking radiation, and we got nonsensical results. We found that in the semi-classical analysis, we were led to bags of gold, where it seems that the black hole can have an arbitrarily large number of internal states, or said differently, an arbitrarily large amount of entanglement with the radiation. We also discussed how there's another possibility, or that one other possibility is that what's happening is we have information loss, that the state of the total system goes from a pure state, say at t equals 0, to a mixed state in the future. We were led to this by assuming that the black hole Hilbert space is finite dimensional, or that it has a maximum entanglement entropy. Then we discussed the possibility of unitary evolution. And then we showed that if we have that, then we are led to firewalls, that the horizon of this wormhole is actually on fire everywhere, and it seems that the wormhole is not really a wormhole anymore. So that was unsatisfactory. And so now the question is, what was our mistake? Where did we go wrong? The claim is that, so the claim is that we've been using the wrong formula for computing the von Neumann entropy of the radiation. In particular, there's another formula you need to use when you compute the entropy in systems that involve gravity. Okay? So at this point, it's ultimately going to be because in the semi-classical approximation, we were ignoring the dynamics of gravity. And even though I'm not going to discuss those dynamics in this lecture, I will show how this interaction with gravity gives us these new results, which I'm about to explain. So for this lecture, I'm going to state the new formula and explain it, and then leave its derivation for the final lecture, as I just said. So let me zoom into this part here. Sorry for moving around. Okay, so what is the statement? So the statement is that suppose we have some region Q, which is any subregion of the path that possibly includes the interface with the ADS spacetime. It's going to be clear from tomorrow's lecture why I'm restricting to subregions in the flat space region. Ultimately, it's going to be because gravity in the ADS region is dynamical, and so it's not gauge invariant to well, maybe that's not the best word. It's specifying a region in the gravity, specifying a subregion in the gravity theory is subtle, well, because gravity is dynamical. So let's focus on subregions in the path. Then the claim is that to compute the entropy of Q, or what is called the gravitational fine-grained entropy of Q, you need to use the following formula. So you need to consider some functional, which is some functional. It has the dilaton term over G Newton plus a von Neumann entropy term so on a surface X, which in this case, well, it's a codimension 2 surface, so it's a point in the ADS region. Plus the von Neumann entropy of some region specified by this X, which I'll explain in a second. You need, okay, maybe I should just read what I wrote and then explain it more later. So X is a codimension 2 surface, which is just a point in the ADS region that is going to have to be homologous to the intersection of the boundary of Q and the boundary of ADS. What this homologous means is that there exists a space-like codimension 1 region in ADS, which I'm calling sigma X, that is bounded by X and the intersection of the boundary of Q and boundary of ADS. Okay, and then you have to just evaluate this functional, take the extremis over these X's, and then you have many extrema. You take the one with that minimizes this functional. Again, you're not supposed to understand everything at this point. I'm going to explain this in great detail. Okay, now let me zoom out. Okay, so let's go through this slowly with some examples. So let's suppose that the region Q is a subsystem or is a subregion at t equals 0 in the right path that contains the ADS boundary. So that's this picture here. Okay. And say this region goes from 0, that's the ADS boundary, up to some point B. The first thing we should explain is this homology constraint. So in this case, the the intersection of Q and the boundary of ADS is simply the right boundary R. So we need to find bulk surfaces or bulk points that are homologous to R. Here I've given some examples for us to analyze. So in example A, the surface X is simply a point. Then the region sigma X is the region which is bounded by X and the right boundary R. So indeed, X and R are homologous. So in the case of a single X, this works. Let's consider the other option of having maybe two X's, so two surfaces in the bulk. Now you can convince yourself that there's no way that these the 3 points x1, x2, and the boundary of R, sorry, and just R, are the common boundaries of a single space-like region. You can just convince yourself of that. So this doesn't work. Option C is where you have three surfaces, three x's, x1, x2, and x3, and it is homologous to the boundary. So
Ahmed, I'm sorry to interrupt you, but could you maybe zoom in a little bit?
Oh, okay.
Because I think it's not so easy to read. Thank you.
Okay. So here it is. So again, it's clear in options A and C that the surfaces X are homologous to R because you can find a bulk space-like region that is bounded by the X's and R, while in option B you can't, and so on. So you sort of see the pattern here. You need an odd number of X's in ADS. Just a comment, these in cases like option C, where you have these space-like regions, I call them surfaces, I meant regions, that are not anchored to the boundary are called islands. So in option C, this region here is called an island. Okay. So any questions about homology up to this point? Or any other questions? I'll wait for 5 seconds.
Yes, sorry. Can you repeat the argument of the B picture? I mean, why is that not homologous?
Because you can't find a surface sigma that is bounded by x1, well, a surface whose boundary is the union x1, x2, and R.
Okay, great. Thank you.
Any other questions?
So there's a raised hand by Human Neshat. Can you please unmute and ask the question?
Yes, so I have basically 2 questions. So the first one is that this new manifold that you have created with adding the flat bath to ADS is not still globally hyperbolic, right? Or is it?
So I'm not making any, well, I mean, you do have a Cauchy slice that goes from this point up to that point, and then from that Cauchy slice, you can determine the entire solution in a big causal diamond. So it's globally hyperbolic in that sense.
Yes, but you're adding the flat space to the ADS one, and your real boundary is still the ADS boundary. No.
I mean, no, I don't follow. Can you explain why this ruins global hyperbolicity?
I mean, the null paths would still cross the ADS boundary
Yeah.
before they cross, for example, that sigma, the time-like curve that you, for example, draw on. For example, if you draw a time-like curve from I naught in the right-hand side to the I naught in the left-hand side, that would be a partial Cauchy surface, but the null paths would still cross the ADS boundary before crossing that line. I mean, are you considering the flat boundary, the real boundary here?
Yeah, you should. Well, I think when you talk about global hyperbolicity in this case, your boundaries are, this is not a boundary anymore. The boundaries are really the square plus and square minus of the path.
Mhm.
I think that's
Okay, I see. Yes, and a quick question: when you mentioned the horizon of the wormhole, do you really mean the horizon of the black hole, or I mean the terminology? Yeah. Yes. What do you mean about that?
For me, these are synonymous. So
Okay.
when I say the horizon or the black hole or the wormhole, I just mean these horizons.
Okay. Thanks.
So Ahmed, there are two questions which are a bit related. One is by Maria van Best, which is in figure B, why can't you connect x2, x1, and r?
Mhm.
And another question by Farad Sokuhi, can you repeat the homologous definition?
Okay, so let me do the second one first, and then the third, and then the first. So the definition of homology is that, well, in this case, that there is a space-like region, a space-like codimension 1 region in the bulk, whose boundary is X union R. Okay, so that's the definition of homology. So in this case, R is this point here, and indeed there exists a space-like bulk surface sigma whose boundaries are X and R. Now let's look at option B. Option B, you might say, oh, let me just consider a surface that goes from X2, touches X1, and then goes to R. That's not, that doesn't fit our criterion, because in this case, the boundary of such a sigma would be X2 union R. X1 would not be part of the boundary. You need a surface that all 3 points constitute its boundary, which is obviously impossible in this case. I hope that answered the questions.
Yeah, I think you can go on. Thanks, Ahmed.
Okay. I'm going to zoom out now. Go to the next page. Yeah, for some reason, I wrote very small this time. Okay. The page on the left is the page from last time. So let's just focus on the right. I'm going to zoom in. Sorry. You know what? Let me just do this. Single page. Okay. So we discussed so far homology. Now let's talk about extremization. So the next step is to consider the homologous surfaces that extremize this functional, which also goes by the name of the generalized entropy. So it's given by the dilaton phi naught plus phi evaluated on the surface X divided by 4G Newton, plus the von Neumann entropy of the region of the union of Q and the region sigma X. So I'm going to go back a slide just to look at the picture and then come back to this. So in this case here, let's look at option A. The von Neumann entropy is going to be on the entire interval from, well, the union of sigma X and Q, okay? Now let me go back to the thing I was just discussing. Okay, so this functional is called the generalized entropy. This first term is often called the area term. In higher dimensions, this would be the area of the extremal surface divided by 4G Newton. In 2 dimensions, that area is replaced by the dilaton. Okay, so we need to extremize this functional. What does that mean? So we say that X extremizes the generalized entropy if the first order variations of the generalized entropy vanish. And here I mean variations in moving the surface. So variation X of Sgen, which you can just think of as the derivative of the generalized entropy with respect to the coordinates parameterizing X, has to vanish. Okay, so this is the extremization condition, and the such X's that extremize functional are called quantum extremal surfaces. Okay, I'm going to use the abbreviation QES for short. And just as a matter of terminology, that you might have heard this somewhere else. Sometimes there's another notion called the classical extremal surface. That's the surface that extremizes only the area term, or only, in this case, the dilaton term. Okay? We will not talk about this kind of surface. The more relevant one is the quantum extremal surface. Here, quantum, it's called quantum, not because the surface itself is quantum mechanical, the surface is still a surface, but it's quantum because it involves a quantum von Neumann entropy of the matter fields living on this background. Okay, so now I'm gonna scroll downwards.
Sorry, Ahmed, there is a question before you go on, but it is on the previous slide. When you were talking about the homology constraint.
Okay.
Yeah, if you can show figure B, the question is why, by Pedro Jorge Martinez, why we cannot think of B as the limit in which x1 in C goes to the boundary. I am assuming something blows up for you if you are at the ADS boundary, but if you could clarify, it would be great.
What do you mean the limit? I didn't understand what was meant by the limit that x1 goes to the boundary. Maybe the speaker can turn on his.
I'm sorry, can I clarify?
Please.
Oh yeah, in the drawing C, let's say you take the limit x1 to the boundary. It kind of makes sigma 1 to 0, so it's kind of a cheat. But if it looks like in the limit as x1 goes to the boundary, C becomes very similar to B.
I would. So are we? Well, B becomes very similar to A in that case.
No, but I'm talking x1 in drawing C.
Ah, okay. So x1 in drawing C. Okay.
You take x1 to the boundary, and it kind of looks like B.
Okay, let me put in another rule. You're not allowed to take the x's to the boundary. They have to be.
Okay. I figure. Yeah. I imagine something like that. Okay. It's because it blows up. Something blows up, right?
Yeah.
Exactly. When you go. Okay. Thank you very much.
Yeah.
Yeah. And Thomas Codina has a. Can you ask your question? You have raised your hand.
Yes. Sorry. In the definition of the generalized entropy, you give it for. I know that we are considering just the degrees of freedom of the dilaton and the metric, but could you make a quick comment about how you will incorporate higher, I mean, some kind of gauge fields or something like that? Or is it known how to include gauge fields or p-forms or something like that?
So I'll make 2 comments. Well, for gauge fields, they would contribute to this term here, to the entropy. So the gauge fields are just going to be just extra matter. So they're going to they're going to come in the von Neumann entropy term. But you can now think of, even though this was not your question, but you can think of more generalized theories of gravity where you have an expansion, an R expansion or derivative and so on. That's going to change the area term to some different functional of the intrinsic metric on the surface. So you can have Ricci scalar terms and derivatives of that and so on and so forth. This generalization is called the Wold entropy. I can put a reference on Slack for that.
Sorry, I mean a higher derivative of the Ricci tensor. I mean higher derivative of metric degrees of freedom are going to appear in the first part of the. You say. I mean, why the dilaton? I don't see why it's going to be equal to the dilaton and not.
No. So far in this theory, this is a very simple theory. That only term that appears in the area term is the dilaton.
Ah, okay. I mean, you're going to have more contribution for for that part. I mean.
Yeah, but in higher dimensions, if you have Einstein-Hilbert, then this becomes just the area. But if you have higher derivative theory of gravity, then this becomes a more complicated functional in terms of the area and the Ricci scalar and derivatives of it, and so on and so forth.
Great, great.
Yeah, and
Okay.
that's this generalization is called the Wald entropy. I should also say that yeah, Wald, W-A-L-D. I'll put a reference. I should say that in this in our model here, well, in higher dimensions, the graviton also, in principle, should contribute to the von Neumann entropy term. Okay, but I'm not going to make any comments about that.
Okay, great.
For our model, we just have dilaton area over 4G Newton plus the von Neumann entropy of the matter fields living on the background.
Great, thank you.
Okay, moving on. So I'm going to scroll downwards. Yeah, so let's apply this to our example. So let's focus on option A, which was the case where we only had a single point X. Due to the symmetry of the problem, you can convince yourself that because Q, maybe I didn't emphasize this enough, Q was a region at a fixed time. It just went from 0 to B with same time coordinate. You can convince yourself by the symmetry of the problem that the surface X can also has to be on that same slice. It has to be on the same at the same time, okay, in the bulk. So you can parameterize it by some location minus A. So A is a positive number here. I'm imagining my coordinate system. If you recall the exterior coordinate system, I had this coordinate Y. This spatial direction goes from minus infinity at the horizon all the way to plus infinity at spatial infinity in ADS, in the flat space region. Okay, so we need to extremize. For that, we need to know what the solutions are. Well, we need to know what the dilaton is and what the entropy is. The dilaton looks something like this. I wrote this down before. The profile, if you plot it, it looks something like this. It has some value at the horizon, and it grows and blows up near the boundary. The matter entropy, which maybe you guys should try to compute by yourselves at some point. All the formulas are in the previous lecture and the problem set. Looks something like this. And what you find if you plot it is that it blows up near the horizon and also blows up near the boundary. And so if you think about this enough, you can convince yourself that there is going to be an extremum somewhere, basically because if we focus on the region near the horizon, the derivative of phi is positive, while the derivative of s is negative. Okay, and so you can hope that there would be a point somewhere here where these two derivatives would balance each other out, and you get that the variation is 0. Okay, so that's how the extremization works for this case. Now let me go to the next slide. So let me go up. Yeah.
Sorry, Ahmed, can I mention some questions to you?
Yes, you can. Although let me just, I think I lost a page. 1 second. Moving. Yeah, go on.
First of all, can you comment on so Ahmed Barbar is asking, is the generalized entropy related to the holographic entanglement entropy formulas like the RT formula and its quantum corrections?
Yes, it is. It's exactly that. I should have mentioned that, although I will make a comment about that later, but it's the same origin.
Okay, I think the other questions have been addressed by Edgar, so we can go on.
Okay, so something you should work out is that there is an extremum at some a. So you take the derivative, set it to 0, an extremum where a satisfies this formula here. Okay, very good. Now let me make some comments about this. I'm going to scroll down quickly. Zoom out a bit. Okay, so you might have been doubtful that an extremum exists because the area term is much larger than the matter term, right? The area term goes as 1 over g Newton, while the matter term is proportional to c, just the central charge of the matter theory. And maybe I was not explicit about this before, but we're working in a limit where 1 over g Newton is much larger than c. Okay. But you shouldn't be worried about this actually, because the extremization is not a balance of the dilaton and the entropy, but rather the derivatives of the two. Okay, so it's something like this: 1 over 4 g Newton, partial a phi plus partial a s is equal to 0. And so the extremum that we found above, in fact, it occurs when the derivative of phi is proportional to g Newton over c. So phi is approximately constant. Okay, that's the idea. So if you go sufficiently close to the horizon, you'll find that the slope of phi is very, very small. And therefore, the extremum is very close to the horizon. And scroll down, yeah. And so you expect that the generalized entropy is dominated by the, first comment is that even at the extremum, so you solve this, you plug it back into the generalized entropy, you'll find that the generalized entropy continues to be dominated by the area term. Here I'm just trying to make a distinction between the generalized entropy and the derivative of the generalized entropy. Okay, so at the extremum, the derivative of the generalized entropy is 0, but the area term, not the derivative, but the actual dilaton, the area term is much larger than the matter entropy. I just wanted to emphasize that point. Any questions up to here?
So I have a question. So how quantum is this? Is this one loop?
Yeah.
Is this one loop, and there could be higher loop corrections?
That's right. Although you can fix that by taking this C to be large. And then it becomes more and more classical.
Okay.
So you can work in the limit where, so the fluctuations in the location of the surface, they're controlled by 1 over C. And so if you take C to be very large, then it becomes classical. But there are also obviously higher order corrections and so on.
So there is a question by Joan Lamadrid. It's a little bit long, so I don't know if it's better if you read it, but okay, I'll try to read it. If we take the B goes to 0 limit on the extremization condition, A still stays finite. So the dilaton is not evaluated at the event horizon as we would expect from thinking about the Bekenstein-Hawking entropy. If phi is not evaluated at the horizon when B is equal to 0, is this generalized entropy still related to the one of the black hole plus the matter CFT? If not, what does it represent?
I will discuss this point in a few pages. Okay, so let's hold off on that for a sec. Okay, no more questions?
No.
Okay, so I'm going to scroll down now. Okay, so the next point, so we found the homologous surfaces. We discussed extremality. The final point is the minimality constraint, okay? Which is a statement that if there are multiple extremal surfaces, remember we had all these different options and so on. If there are multiple extremal surfaces, then the entropy of Q will be given by the one with the smallest generalized entropy. Okay. So in our example, the one we just discussed and are still discussing, there are no other non-island extremal surfaces. So there's only one location where a single X can be extremal. Now you can look for island contributions. So like the picture I have here. And even though this was not analyzed to death, I believe that there are no extremal islands. There are no examples of this sort for this interval Q that are extremal. And even if there were, this is just a general point, which we'll come back to later, that if you have an island contribution like this, these are disadvantaged when applying the minimality constraints. The reason is they have multiple area terms, right? So there's an area term here, there's an area term here, and an area term there, and they all go as 1 over g Newton. So they're very, very large. And so it seems plausible that they would always be beaten by the case of no island with a single x, because adding these guys can only increase the entropy. Although I will give you a special case where this intuition fails. So any questions about minimality? Okay, so I will move on. So let me make some comments. I guess this is address the last question maybe. So the location of the quantum extremal surface that we found, so we just finished this example. The location, we only found there's only one quantum extremal surface, and we found it to be near the horizon. Okay, so that the entropy now of this region Q is can be well approximated by the area term or the dilaton term, which is approximately given by the Bekenstein-Hawking entropy. Okay. For small b, when you take the limit, or when Q limits to the right boundary, this result is very similar to computing the entropy of the right boundary in just standard holography without adding this bath region in the eternal black hole. So here I have, so here's the eternal black hole with no bath. It has a quantum mechanical boundary dual of just two quantum mechanical systems, L and R. The usual RT formula and its generalizations give you that the entropy is given by the horizon H. Okay, so this is the extremal surface in this case. This is sort of approximately what we have here, where now in the holographic description, we have these two bath CFDs that are coupled to the left and right boundaries. And the entropy that we're computing in this limit as b goes to 0, we're essentially computing the entropy of R by itself. And again, we find that the entropy of R there's some quantum extremal surface, but the quantum extremal surface doesn't quite hit the horizon. Okay, so it's a little bit outside. I'm not going to discuss this in my lectures, but you can interpret this this gap here is important for sort of transferring information, for doing some sort of teleportation protocol where you transfer information from the right-hand side to the left-hand side. But I'm not going to make any comment about that. Any questions about these final comments?
So Ahmed, there's a question from YouTube. It's not by Nadav Bruckner. Can you elaborate on the computation of the dilaton? I'm not entirely sure which part of the computation.
The dilaton equation and its solution and its background and so on was discussed in my first lecture. So I would refer you to that. Any other questions?
I do not see any other questions, so I think we can go on.
Good. Okay, so let's move on. I'm going to scroll downwards. So that was one example. Now let me discuss a different example, a more interesting one. So let's take, in this case, Q to be the union of two bath regions, Q left and Q right, and we want to analyze the evolution of the entropy of Q as a function of time. So we're going to move it upwards on both sides. From the sort of holography intuition, you can think of this as computing the, well, it's the entropy of the left and right boundary quantum systems, which you might want to call, we're computing the entropy of the wormhole. Okay. And so there are two relevant surfaces to consider, or configurations of surfaces. There's option A, which I will call the disconnected surface. That's the one where you have two x's, x left and x right. X left is homologous to this boundary, x right is homologous to that boundary. So this satisfies that. Or the trivial surface. The trivial surface is always there. The trivial surface is the case where there's no x. And you can check using the criteria that I defined earlier. This surface satisfies all of them. By this surface, I mean the no surface. So the sigma in this case would just be a space-like slice connecting the left and right boundaries. Okay, so I have two options in this case: a disconnected surface and a trivial surface. I'm going to scroll down. Let's look at the generalized entropy for these two options. So we have something like this. Okay, so option A, the generalized entropy is going to be the dilaton at these 2 points plus the von Neumann entropy of the union of sigma L, QL, sigma R, and QR. But this is a two-interval entanglement entropy. Okay, so we should be a bit wary of this. We'll come back to this in a second. For option B, there is no area term. There's no dilaton term. It's just the von Neumann entropy of the region going, of the union of QL, sigma phi, and QR. This is a single interval entropy, which, if you remember from from the first lecture, we actually computed this. So this is it. So this trivial surface we didn't see before. That's why I have new here. The trivial surface is always an extremal surface because there is no dependence on there's no dependence on the location of the surface. So the derivative with respect to the surface is just zero by definition. It's automatically extremal. Let's scroll down a bit. And as I said, we computed this thing before. The entropy for B, in the option B, is just given by this C log cosh, which at late times grows linearly with time. Okay, so we saw this before. So that's option B. Now let's discuss option A very quickly. I'm going to scroll downwards. Okay, so for option A, the generalized entropy needs to be extremized with respect to both x left and x right. Okay, this is hard. This procedure is hard in general because of the two interval entropy that appears in the formula. However, luckily, a simplification happens at late times when when Q is evolved to the future at late times. You can show that that there's an extremum. So let me first summarize it, then go through the equations. There's an extremum where there's an extremum in the limit in some OPE limit of the 4-point function. Okay. The basic idea is the following. So in the matter entropy calculation, it's a 4-point function of it's a 4-point function of twist fields located at y1, y2, y3, and y4. At late times, of this 4-point function, if we, well, let me see, what's the best way to say this? Well, okay, so at late times, you can show that it is consistent. Well, at late times, you end up in this OPE limit where y1 goes to y2 and y3 goes to y4, such that this 4-point function factorizes into the product of two 2-point functions. But if the 4-point function of the twist field factorizes, this means that the entropy of the two intervals becomes simply the sum of the entropy of the one interval case. Okay, so this is what happens because of this. I discussed this briefly in the first lecture. So this means, I'm going to scroll down a bit. So this means that the generalized entropy in this situation at late times breaks up into a left and or into left and right pieces. In the option A, the generalized entropy becomes a generalized entropy on the left plus a generalized entropy on the right. This means that we have two copies of the single-sided example that we already did. Right? Therefore, there's an extremum in this case, as we just showed, and the generalized entropy is just going to be given by twice times the Bekenstein-Hawking entropy, approximately. Okay, any questions up to this point? Are there questions?
Yeah. So Ricardo, can you please unmute?
Yeah, sure. Are those twist operators in the gravity part the same as the ones that are in the non-gravity part, or are they related somehow?
Here, I mean, we have the same CFT living everywhere. It's just that the metric changes. So when you compute, maybe the quick answer is just yes, but it's the more careful thing to do is to say that when we compute this 4-point function of twist fields, we implicitly did this conformal transformation or this Weyl transformation that I discussed in the first lecture, where you first go to a frame where it's flat space everywhere. Then it's just the same CFT everywhere, and so the twist fields are the same everywhere. As in, it's the same field, but just evaluated at different points. That's how you should think about it.
Thomas Codina has raised his hand, please.
Yes, my question is, what are you losing taking this limit? I mean, it seems that simplifies the calculation considerably, but what are the implications? I mean, what are you losing doing this late time limit?
So,
can you go back to a generic timing in a way or something like that?
So this, when you take an OPE limit of a 4-point function, you're making an approximation to the 4-point function. So the 4-point function is equal to this plus other terms.
Yeah.
Other terms are large at early times, but at late times they're small. And the smallness is controlled by by how close y1 is to y2 and y3 is to y4 and so on. It's controlled by the OPE, by the conformal ratio.
Okay.
There's a question by Farad Sohukuhi. Is the extremization of the surface only needed when there is an area term? So in case B, that's why you don't do it?
Correct.
Well, Edgar just replied.
I hope Edgar and I agreed on that answer. Okay, so moving on, we're almost done. I'm going to scroll downwards now. So far, this is what we found. So in option, so here I'm plotting the entropy as a function of time for the two answers that we got. There was the trivial surface calculation, which was log cosh, which became a linear growth. And so that's this thing. So that's the trivial surface contribution. And we also found this other contribution, the disconnected surface, which is approximately given by twice the Bekenstein-Hawking entropy. There's some time here where it begins to exist, or where you can show that it actually is an extremum. And this is what I meant by the late times, when that OPE limit becomes valid. And so we have two answers, or two contributions. And now we can apply the minimality constraint. I think I can zoom out for this lecture, for this page. Okay, so we can apply the minimality condition here, and we get the page curve. But the entropy of Q left union Q right is going to be the minimum of these two curves. And so before the page time, before these two curves intersect or cross, the entropy will be given by this linear growth, while after the page time, the entropy is going to be given by twice the Bekenstein-Hawking entropy. Okay, so success, this magical formula that I proposed gives us gives us a consistent answer for how we should expect the entropy of the black hole to evolve in time. The next slide it's going to be brief. It's going to be about doing the same thing but for the radiation. But before I get there, are there any questions about this point? Okay, very good. So I'm going to scroll downwards now. So this is the final example, which is to compute the entropy of the two bath regions that contain the Hawking radiation. This is essentially the complement or the bath complement of the previous case. There are two options now for applying the formula. You can have the option where you have an island. So you can have the extremal surfaces in the bulk, as shown in option A. Or you can have the semi-classical or the trivial surface contribution, where there's nothing in the ADS bulk. And the generalized entropy of option A is going to be the area terms at the location of the area terms of the x's or the dilaton, plus the von Neumann entropy of the union of Q bar and the island. And for the trivial case, it's just going to be the entropy of Q bar by itself. Okay? And you can convince yourself, I'm going to scroll down a bit, that this is identical to the previous case. Why? Because the matter state, the global matter state going from one infinity in one bath region to the other infinity in the other bath region is pure. Therefore, the entropy of Q bar sigma island Q r bar is equal to the von Neumann entropy of QL union sigma left, union sigma r, union QR. This is the entropy that appeared in the previous calculation, and similarly in the trivial surface case. So we don't need to do the calculation again. We know what the answer is. I'm going to scroll downwards. Let's see, zoom out a bit. So the previous argument, the previous point, I argued that the entropy in the case, well, the entropy of the black holes or the wormhole is equal to the entropy of the Hawking radiation from the get-go. Without doing any calculation, we know that this has to be true. And therefore, the page curve of the black hole is the same as the page curve for the radiation. So we have this growing entropy piece, which is captured by the trivial or the no island or the semi-classical surface. And we have this constant piece, which is like the disconnected or the island contribution. And so we can declare victory at this result. Let me make some final comments, which is that so at early times, what we find is that the entropy of the radiation is captured by the semi-classical result. So that means it just grows linearly, basically because of the entanglement between the interior and exterior. And it stays like that up until the entropy is large. By large, I mean when the entropy is comparable to twice times the Bekenstein-Hawking entropy. Then at that stage, there's a transition, and the entropy is then captured by the island contribution, which says now that the interior modes, actually, maybe I can show you two pages at this point. Yes. So the second point here refers to the second picture here. So the island contribution tells you that when you compute the entropy of the radiation, you also need to include the island. Okay, so this is after the page time. And therefore, the entanglement between the Hawking quanta in the island and those outside in the bath or in the region Q don't contribute to the entropy of the radiation. And that's why the entropy is small and doesn't grow at late times. This can be interpreted, well, first of all, this result is consistent. The results we've been finding are consistent with unitarity, thankfully without running into firewalls. You can the reason why this is happening, you can think of what's going on is something like ER equals EPR, that the interior is secretly part of the exterior. I'm pretty much done. I just wanted to point to this picture up here, which explains why we don't have the bag of gold issue, which is really the same thing as what I said at the bottom here, but that the entropy of the boundaries, Q left and Q right, or left and right, the reason why it doesn't grow is because it doesn't include the region inside the black hole, and therefore you don't include all of the interior Hawking quanta. And that's all I had to say. Thank you.
Okay, let's thank Ahmed. So questions? So Ahmed, let me start with a question from YouTube. So Nadev is asking, do we know that there isn't a smaller result when we add more islands?
Yeah, so I had an argument like that for the previous case of computing the entropy of only one region of an interval on the right bath. But this is a special case where the island does come in. The reason is that the naive, well, not the naive, but the contribution without the island, it continues to grow for all time. At some point, it becomes convenient to add the island contribution. But I think generically you don't, well, I mean, I don't know what I mean by generically, but in most cases, the island is not important, but this is a special case where it is.
Okay, Ricardo Espindola, can you unmute yourself?
Sure. Can you explain a little bit what is the causality paradox that appears when a signal from the boundary reaches the piece of the island that is outside of the horizon?
So the causality, you said causality paradox?
Yeah, if there any causality issue there.
So far in what I discussed, well, good. So you can try to think of doing some sort of special experiments that naively might lead to a paradox. For example, you can decouple the ADS region from the bath region, but then still have the island be part of the bath region and so on. You can do experiments like that or calculations like that, and you don't seem to find a paradox. Somehow gravity is always smart enough to avoid running into these paradoxes. I don't have time to go into that in detail, but I will put a reference in the Slack for some quick investigation into this question. But so far, there don't seem to be any causality paradoxes.
Can I ask you a question?
Yes.
Is there some way to relate this to the work of, say, Papadodimas and Raju, meaning the exterior and interior somehow?
Yeah, well, yes.
And the interior is somehow part of the exterior or something like that. I mean, the interior is smaller.
Let me make some points. Although we'll hear more about this tomorrow. I will say something brief tomorrow, but Douglas will say more. That you can find a dictionary between the physics in the island and the physics in Q bar outside here. There's so you can find the operators which, when you act here, they can create something in the island. And the properties of these operators are very similar, or they share some features with the proposals of Papadodimas and Raju, where, for example, you have this property of state dependence. And for different microstates of the black hole, you need to use a different dictionary and so on. The reason why I said ER equals EPR here is just because of the emphasis in that the thing that makes this happen, the thing that gives you, that generates this non-local identification between the inside and outside, it happens when you build up enough entanglement. Yeah, so it's sort of special to that case, but ultimately the mechanism in both these examples, ER equals EPR and Papadodimas and Raju, the proposals and many others, Bermudez as well, is going to be realized by this dictionary that's going to be discussed tomorrow, mostly by Douglas.
So are there any other questions? I don't see anything in the chat or on YouTube. Oh, yeah, Ricardo, please go ahead.
In pen and paper, you need to, or in this hidden particle protocol, you need to wait until the scramble time for the information to go out. Is there any analog here in this construction, in this toy model?
Yes, there is. So I'm going to go back a few slides. Sorry. I might talk about this tomorrow, so let me just go back quickly. So I'm going to zoom in now. Okay, so let's look at this situation where we only compute the entropy of a single region in one bath. There's a notion which, as I said, I'll mention briefly tomorrow, maybe, that there's it's related to what Matish mentioned, that there's a sub-region duality here, that there's something that goes by the name of entanglement wedge reconstruction, which says that the physics of the region sigma, the bulk, is actually captured by the region Q on the boundary. Okay, so there is so any information here can be learned by doing experiments purely here. Okay. Now, suppose you throw a message in from the boundary. So suppose I throw a message in like this. If I throw it in from this point, it'll at t equals 0, it's going to be somewhere here. So that message can be reconstructed from Q. But now if I throw a message from a much earlier time, so somewhere here, it's going to fall into the black hole, and at t equals 0, it's going to be completely missed by the region sigma. It's going to be outside of the region sigma. So that message is not contained in the region Q. So there seems to be a time here before which, or I guess after which in this case, the message can be learned or reconstructed from Q, but before which it cannot. And that time, you can calculate this and find that it's precisely the scrambling time. So if you throw a message into the black hole, in this case, and you wait a scrambling time, this region loses access to that message. And it has to do with the fact, well, if the message is not reconstructible in here, then it's reconstructible in the complement of the region Q. So this is sort of, it's a demonstration of how when you throw, it's a demonstration of the Hayden-Preskel protocol, where you throw a message into a black hole after scrambling time, or a few scrambling times or whatever, then the message can be reconstructed not from the black hole, but from the complement of the black hole, which is the radiation. In this case, the complement of Q is the union of the radiation here, plus the entire left system. So that's my brief comment on this.
Thank you.
Okay, I do not see any other questions. So let's thank Ahmed again for the nice lecture. So we'll reconvene in 1 hour and 45 minutes.
Thanks, Ahmed.
Yeah.
Hi, Kyriakos.
Oh, hi, Douglas. Hi. How are you?
Good, good. Thanks. How are you?
Great lectures so far.
Thanks. Is the screen okay? Is it?
I think it's great. Yes.
Okay, good. Make sure this is...
Douglas, are you ready to start?
Yeah, I'm ready.
Okay, great. So we continue with the third lecture by Douglas on more on quantum black holes.
Okay, great. So we're going to move to a second topic now, which is going to occupy us for today's lecture and Friday. And again, the idea is to try to reinforce some of the material that Ahmed is discussing in his lectures. So today, Ahmed introduced the island formula and discussed some applications of that. And we're going to discuss the island formula in a very simple model of JT gravity. We'll be able to do some computations in a lot of detail, especially on Friday. Today, we're mainly introducing the model and discussing some simple computations. And on Friday, we'll do a more detailed analysis. So before we start, there's two things that are going to be helpful to just have in mind for the rest of the lecture. So I'm just going to start by introducing those. So suppose we have an entangled state of two quantum systems. Here's our state psi. It's a sum over k different terms of state I in system 1 and state I in system 2. So this describes an entangled state between system 1 and system 2. We're summing over all k of these terms. And this particular state, where the coefficient in front of each term in the sum is equal, in this case, it's just 1 over square root of k. That type of state is called a maximally entangled state. So that's our state psi. And what I'd like to do is review the entropy of either of the systems, 1 or 2 in this maximally entangled state. So to compute the entropy, we first compute the density matrix of one of the systems. So for example, well, it's the same either way, but let's say we're computing the density matrix of system 1. Then if you start with this state here and trace out system 2, you find this density matrix, 1 over k times the identity matrix. So this is a feature of the maximally entangled state, that when you compute the reduced density matrix for one of the subsystems, you get a multiple of the identity matrix. So it's a very simple density matrix. Anyhow, if we compute the entropy of this density matrix, we use the handy formula. Von Neumann entropy is equal to minus trace of rho times log rho. And we can just do that explicitly with this matrix. We find minus 1 over k, that's the rho factor, times log of 1 over k. And if we sum that over k different terms, we find the answer log k. So the entropy of the maximally mixed state on k different individual states is log of k. Okay, so that's a useful thing to keep in mind. And it's also useful to think about a slightly simpler measure of the entanglement, which is sometimes called the purity. So that's just trace of rho squared. The simplest property of rho, right, would be trace of rho, but that's equal to 1. That's just the normalization of the density matrix. The second simplest aspect of the density matrix rho would be trace of rho squared. And we can use that as a kind of measure of the entanglement. If we compute trace of rho squared, we find a sum over k terms of 1 over k squared, because the individual terms in rho are 1 over k. So the answer is 1 over k. So a handy thing to keep in mind is to remember that a small value of this purity, a small value of trace rho squared means a large entropy. Okay, so entropy is log k, purity is 1 over k. Okay, so that's one of the two things I wanted to remind you of. The other thing is the following. On Monday, we were thinking about the partition function of JT gravity, and we computed it in a classical approximation. So we computed z of beta. And one of the things we did with z of beta was we computed the entropy by using the thermodynamic formulas, first computing the entropy, the energy, and then subtracting that to get the entropy. There's actually a shortcut to compute the entropy directly, which I'm sure many of you are familiar with, at least in higher dimensional cases. The way you compute the entropy of a black hole normally is you take the area of the horizon divided by 4 times g Newton, a very famous formula for the Bekenstein-Hawking entropy. In dilaton gravity, the analog of that is to take basically the value of the dilaton at the location of the horizon. The dilaton plays the role of the area. So in higher dimensions, we take area divided by 4 g Newton. And in dilaton gravity, we take the value of the dilaton. I think Ahmed explained that in his lecture earlier today. But anyhow, in the conventions that I'm using, what we're supposed to do is we're supposed to take S naught plus 2 pi times the value of the dilaton at the horizon. And that gives the entropy of the black hole. And if you work this out using the classical solution that we discussed on Monday, you'll find that the entropy we computed, which was S naught plus 2 pi squared over beta, is in fact equal to this expression here. So the S naughts clearly match. And the one thing you have to check in the calculation is that the value of the dilaton at the horizon is pi over beta. Okay. So actually deriving this shortcut for computing the entropy will be part of a more complete calculation that we do on Friday. But for now, it's a good idea just to keep it in mind. Okay, so those are our two pieces of preparation. And now we can get into the good stuff. So here I've taken I've stolen a picture from Ahmed's second lecture. So this is a drawing that he made of a problem that he introduced as the bag of gold problem. So this is a two-sided black hole. These triangles here are the Minkowski regions that Ahmed is using as a bath on the right and a bath on the left. And the region inside is the black hole. And these squiggly features here represent excitations of the quantum field, so the Hawking radiation. The Hawking radiation outside in the bath and the partner modes behind the horizon. So as Ahmed explained, the problem here is that if the black hole is late, this slice is very late, then you can have a huge amount of quantum fluctuations behind the horizon. This becomes very wide. You have a huge amount of entropy back here, entangled with stuff outside the horizon in the bath region. So as this slice becomes later and later, the problem is that you can get an arbitrarily large amount of entanglement between stuff outside the black hole and the interior of the black hole. And that's a problem because the amount of entanglement could exceed the entropy of the black hole. So this is the bag of gold problem that Ahmed explained. Now he drew it for a two-sided black hole, but we can discuss a slightly simpler but very similar problem for a one-sided black hole. And the way we make a one-sided black hole is we just take the drawing that Ahmed made and we cut it in half. Or more precisely, we take a Z2 quotient, where the Z2 interchanges the left and the right sides. Another way of saying it is that we take the space-time, we cut it in half, and we put an object there that called an end-of-the-world brane. And the rules for the end-of-the-world brane is that the space-time is allowed to just end at the location of the end-of-the-world brane. So instead of having a complete two-sided picture like this one, we cut it in the middle and we put an end-of-the-world brane there. And now we just have one region outside the horizon of the black hole. But we still have the same problem, which is that there's a lot of stuff behind the horizon that's entangled with stuff in the bath. Okay, so this is the bag of gold problem in the case of the one-sided black hole. All right. So we're going to take that picture that Ahmed has been working with, and we're going to study an even slightly simpler case. The case we're going to study is shown here on the right. So this type of drawing is going to come up a lot of times in today's lecture, so let's make sure that we understand it. The most essential feature of an Ahmed setup is that there's a lot of entanglement between things behind the horizon of the black hole and stuff outside the black hole in the bath region. In the case Ahmed described, that entanglement is created by the dynamics of the quantum fields. We're going to be a little bit, well, a little bit more crude, and we're going to put the entanglement in by hand. So here's a drawing of a one-sided black hole with an end-of-the-world brane shown in blue. So it's similar to the geometry at left here. The difference is that this black hole, we don't have this Minkowski space bath region. It just ends at an ADS boundary. So the drawing I've shown here is very similar to this portion of Ahmed's black hole. Okay, and to create the entanglement, what we're going to do is we're going to imagine that the end of the world brane can have a lot of different internal states. So it's sitting there as some object that ends space-time, but let's imagine that there's a lot of different flavors of end of the world brane, k different flavors of the end of the world brane. And so we can have many different internal states of this object. So those different internal states can be entangled with some other system R, which is outside the black hole. The system R is going to play the role of the bath in Ahmed's setup. So we have some bath outside the black hole, and it's entangled with the choice of which state of end of the world brane we have behind the horizon. Okay. So the full state of the system that we have, psi, will look like the following. It's going to be a sum over I from 1 to k of, first of all, a state I of the R system. By the way, I'm calling it R to mean radiation, like Hawking radiation. So the radiation system is out here, outside the black hole. And we have state I of the radiation, and it's accompanied by state psi I of the black hole. And what does psi I mean? It means a state of the black hole where the end of the world brane is in state I. So we have the same state for the end of the world brane as we have in the radiation, maximally entangled state between the radiation and the end of the world brane. And the whole state of the system looks like the state of the black hole in which the end of the world brane is in state I, tensored with the end of the world brane. Okay, and we're going to consider the case where this entanglement is maximal entanglement between all k different states of the end of the world brane and k different states of the radiation. So if you remember from a couple slides ago, naively, we would expect that the entropy of this arrangement would be log of k. So we have k different states here. Okay, so this is a, I want to make sure that this setup is clear before we go on. So if anybody would be willing to ask a question or clarify something, that would be really helpful at this point.
Are we assuming that they have the same number of states?
Yeah, so Yes, yes, we're assuming they have the same number of states.
Ricardo, please go ahead.
Yeah, what do you mean by IR? So are you changing the radiation system, which I mean, degree of freedom at the end of the world brain?
Okay, good. So so the IR is a state, not of the end of the world brain, it's a state of the radiation. So let's imagine that we have some box over here that contains some system that can be in K different states. So the radiation system R could be in any of K different states, and those are labeled by I sub R. And so you could imagine some qubits out here or something like that with many different possible states, and the states I sub R just represent the different states of these qubits. And the main point of this state is that we're taking each different choice of state for the R system, and we're tensoring it with a different choice of state of the black hole. And the different choices of state of the black hole are different only in the end of the world brain is in a different internal state. Yeah, it's a bit of a strange setup, but.
Yeah, so there's a question from YouTube by Nadav. Do we take log K to be the area law?
No. So it's the interplay between log K and the area law will be the main focus of our talk, but they're different, and we'll have to understand what happens between them. But that's coming later.
So I also have a question about this. I guess at this point, we're not very specific about the nature of those states, K, I mean the end of the world states. But I guess they're not, they're time-dependent states, right? Or from the way that the diagram is drawn, they seem to be energy eigenstates.
Yes.
But should we be thinking them of spanning the Hilbert space of states of a given energy? Can I think of them as maybe an over-complete base of states?
That's a good way of thinking about it. Yeah, exactly. So they are some states at some energy. They're time dependent, and we're choosing K of them. And they're not necessarily orthogonal. They're just some set of K states. And if we choose K to be very large, then they'll be over-complete.
And there is one more question from Nadav. How do we incorporate the entropy growth? Do we have some sort of emission as a function of time?
Okay, good question. So in this model, we don't have emission as a function of time. This model is supposed to represent the picture on the left at some fixed time. So in Ahmed's discussion, as time goes on, you get more and more of this entanglement, more of the radiation. In our model, what we would do is we would just say K is a variable parameter. You get to choose K. And to mock up the black hole at very late time, you should choose a very large value of K. But K doesn't change with respect to the time evolution in this system. To mock up the time evolution in the actual black hole, you just increase the value of K.
So Douglas, do we have time for 2 more questions?
Yeah, sure.
Yeah, so Hamid Dafsar is asking, does the end of the world brain represent the island?
No, it doesn't. Let me explain the island in a moment.
Okay, and then another question by Monire Ahmadpour. Do we have the system R on both sides?
Okay, so we could have drawn a 2-sided black hole, like in Ahmed's lectures, and then have 2 R systems. But here we're just doing a single-sided black hole with just 1 R system. Makes the drawings a little bit easier. Okay, so let me go on. So our goal in analyzing this model is to reproduce the island formula that Ahmed introduced this morning. So the island formula that he wrote is basically this: the entropy of the R system should be the minimum over extremal surface of extremizations over the location of the island I. of the following expression. We have the area term divided by 4g Newton plus the bulk entropy of the R system together with the island. This would be the higher dimensional formula where the entropy of the black hole is area divided by 4g Newton. For the case of dilaton gravity, JT gravity, like we're considering, this term here is replaced by S0 plus 2 pi times the value of the dilaton. Ahmed was using slightly different conventions for the dilaton. I think he had phi naught plus phi divided by 4g Newton. That's just because we're using slightly different normalization for phi. But in this lecture, the first term is S0 plus 2 pi phi. Okay, so let's see what this looks like in the present context, in the context of this model. So here in this purple region, I've drawn the system R, and we're interested in computing the entropy of R. So first, let's consider the case where there's no island. So we apply this formula to the case where there's no island. Then the contribution to the entropy, we get 0 from the area term. So this first term is 0 because there's just no island at all. And the entire contribution comes from the bulk term, S bulk of R union I, but we've assumed there's no island, so it's just S bulk of R. So that's just the entanglement between R and the end of the world brane. And that was maximal entanglement on K states, so the value is log K. Okay, so the contribution if there's no island is log K. But let's also consider the possibility that there's an island. And the island will have its boundary at an extremal surface, at an extremal point of this quantity. And you can check for this black hole that that's the horizon. The island will look like this, the region behind the horizon of the black hole. That will be the extremal point. And let's try to evaluate this expression for that configuration of the island. So now we have a non-trivial island, so there's a first term that's non-zero. And its value is S0 plus 2 pi times phi at the boundary of the island. Boundary of the island is this black dot here, which is the horizon. So we get the contribution S0 plus 2 pi times phi at the horizon. And that's just the entropy of the black hole, as we discussed a moment ago. So the first term here gives the entropy of the black hole. What about the second term? Now we're supposed to compute the bulk entropy of a system that consists of the radiation, that's this purple region here, together with the island. So both of the purple regions together. What is their entropy? Well, you can see that the purple region contains both the radiation and the end of the world brane. So it contains both of these two systems that are entangled with each other. So the entropy of the combined system is actually 0. It's a pure state. It's an entangled state between the island and between the end of the world brane and the radiation. But the joint state of the two systems is pure, so its entropy is 0. So actually for the second case where there's an island, this term is 0. And we find just S Bekenstein-Hawking, entropy of the black hole. So the final step in the island formula is we're supposed to take the minimum over the possibilities. So we have two possibilities here. One gave log K and the other gave S black hole. So the prediction of the island formula is that the answer for the entropy should be the minimum of these two, the minimum of log K and S black hole. So our goal is to derive these answers for the entropy from the gravity path integral. So we want to derive this formula from the gravity path integral. All right, so let's start by explaining this JT gravity setup a bit better. We're going to be working with JT gravity, the same theory we've been discussing so far, but with a new ingredient, which are these end of the world branes. The complete action for JT gravity plus the end of the world branes is shown here. We have the action of JT gravity, which we've discussed in the previous 2 lectures, plus a new term, which is the tension of the end of the world brane. So mu is a tension parameter, and the action of the end of the world brane is just its length, integral of ds. So this would be the same action that you would have for a massive particle with mass mu. So the end of the world brane behaves like a massive particle. The classical solution of this theory in Euclidean signature looks like what's drawn here below. The classical solution for just JT gravity was a red circle. Remember, this red boundary represents the regularized boundary. It's at some finite but large location in the hyperbolic disk. The new ingredient when we add the end of the world brane is that the red boundary can be interrupted. And we have a blue component of the boundary where the end of the world brane lives. So this is the actual boundary of JT gravity, this red region. And this blue thing here is the end of the world brane. And it follows a geodesic. Why does it follow a geodesic? Because its action is that of a massive particle. Its action is just the length. And the solution to the equations of motion that you get for a massive particle is a geodesic. So this blue curve is some geodesic, and the red curve is a circle, part of a circle in the hyperbolic plane. So that's the classical solution in Euclidean signature. So we're going to draw that kind of picture, but a little bit simpler. So I'm going to leave off the angels and demons, and we'll represent what we showed on the previous slide just by this picture here. In Euclidean signature, this is what we showed just a second ago. And if we look at it in Lorentzian signature, then we get this configuration here. You'll notice that the horizontal slice through the middle of this drawing here is the same as the horizontal slice through the middle there. The difference between the two drawings is that we start with that t=0 slice, and we advance in Lorentzian time on the right versus Euclidean time on the left. Okay. So as we said, we're going to allow this end of the world brane to have k possible internal states. We're going to study this entangled state where the end of the world brane is in state I, and it's entangled with some auxiliary system R for radiation that's also in state I. We sum over I. So psi I is a state of the black hole where the end of the world brane is in state I, and I itself is some set of orthogonal states of the R system.
Douglas,
Okay.
can I ask some questions before you go on?
Yeah, sure.
Yeah, so Aranya Bhattacharya asks, is it generally true that the island purifies all the radiation states?
Oh, it might not be true that it completely purifies it, but if it's a useful island, it will mainly purify it. It will purify it almost completely, maybe not completely. In this model, it's simple enough so that it completely purifies it, but it's a good question.
Okay, then Hamid Afshar asks, the boundary of the island is the quantum extremal surface, not the horizon, right?
In general, yes, but again, in this case, so what's the difference between a quantum extremal surface and a classical extremal surface? The difference is that one of them is an extremal point of the area. The other is an extremal point of the area plus the bulk entropy. In this model, we don't have any propagating bulk fields. We just have this end of the world brane. And so the bulk entropy is locally a constant function. So that means that an extremal point of the area is the same thing as an extremal point of the area plus the bulk entropy. So quantum extremal surfaces and classical extremal surfaces in this simple theory are the same. And the horizon is a classical extremal surface. So it's also a quantum extremal surface.
And finally, there is a somewhat longer question by Pedro Jorge Martinez. Pedro, do you want to ask the question maybe using voice, or should I read it?
Yes, no problem. I can do it. Can you go back a few slides when you did computation? One more, please. Okay, that's it. Well,
okay.
Yeah, maybe I'm misunderstanding the computation, but the one with the island, you do not fully get the end of the world brane. Like you do not get the complete, when you, in the shadow part in the island, you do not get the full end of the world brane. So in the sense that there are.
Okay, yeah, I understand your question. I think your sound just cut out, but I'll try to answer the question. I think what you're worried about is the fact that the end of the world brane up here, the part of the end of the world brane up here is not in the purple region. Good. What that reflects is that that end of the world brain up here in principle could be affected by stuff that came from the bottom right of this diagram. So the island doesn't know exactly what's going to happen to the end of the world brain up here because some stuff could come and hit it from the boundary. But the island contains enough of the end of the world brain to capture the entanglement with the R system. And that's all that's important. Is that
okay.
the island purifies R.
I'm sorry, is there an interplay? If I put the end of the world brain closer or farther away, is there an interplay, or is it something that I just see from the drawing because it's very
I think as long as the island contains the end of the world brain at t equals 0, it will be fine. This argument will go through the same way.
Okay, thank you very much.
Okay, one final question before we go on. So Nava Gadam is asking, the boundary of the island appears to be the bifurcation point, not the horizon, which is the dotted line. Do you distinguish between these? Sorry, can you hear me, guys?
Yes. Yeah. We can hear you, but we don't see Douglas.
What happened to Douglas? Douglas, are you there?
I think he disconnected.
Yes, Douglas is disconnected.
Well, we can wait a little bit, I guess, if you reconnect.
I sent him a message. Douglas says to take a 3-minute break. Did you hear me, Kyriakos?
Yes, this is his new version of walking away.
Kyriakos, can you hear me?
Look like he hears. Yeah, I think we should.
Okay. We'll just wait for him then. Yes, I can hear you. Can you hear me?
Yes, yes. I was just saying that Douglas says to take a 3-minute break.
Ahmed, can you hear me?
Yes, I can. Can you hear me?
Yeah, I can hear you. So we're waiting for Douglas to come back, right?
Yes, he'll be back in 3 minutes.
Okay.
Sorry, folks, my internet died, but it's back online now. So let's continue to have another 2-minute break and then we'll restart.
Okay, great.
Okay, so are there some other questions that I can answer before we restart?
No, I do not see any other questions at the moment.
Okay, I think I was in the middle of answering a question when my internet cut out, but I don't remember, unfortunately, what it was. So if somebody wants to re-ask that question, I'll take another shot at answering.
Maybe the question was by Neva Gadam, that the boundary of the island appears to be the bifurcation point, not the horizon, which is the dotted line. Do you distinguish between these?
Okay, yeah, so you're right. This is a sort of a terminology point. People often refer to the horizon either as some point along the horizon or as the whole horizon. And here I'm using the terminology where the horizon is just some point along the horizon, in particular this one.
Okay, and one final quick question before we move on. Does the wiggly horizontal line represent the singularity?
Yeah, it does. And there's no singularity in JT gravity, but I've drawn the wiggly horizontal line there just to orient you in case you're used to seeing such things in Penrose diagrams of black holes. Okay. In Ahmed's lectures, he's a little bit more honest and he draws this thing continuing upwards with no singularity, but I prefer to be a little bit dishonest, but maybe more representative of the higher dimensional case. Okay, so let's get started now. We explained the state, we explained the geometries that were involved, these end of the world brane geometries, and we have an entangled state at the end of the world brane and the radiation. Our goal is to compute the entropy of the radiation. And in this discussion, the bulk geometry is kind of a slippery concept. It's going to change and move around depending on exactly what we're computing. So it's best to anchor our thinking in terms of boundary conditions rather than bulk geometry. So let's get some practice with the boundary conditions. So first, let's consider this Euclidean solution, which we discussed before. I just rotated it by 90 degrees. Here's the end of the world brane, and here's the boundary. This is a solution to the following boundary problem. The boundary problem is drawn with this notation. What it means is the black line here is some location where the length and the value of the dilaton are fixed. The black line has some fixed large length, and the boundary condition is that we should have a boundary with a length of this long and a particular value of the dilaton. And then I draw these blue circles here at the endpoints of this black line. And at the locations, the blue circles, the requirement is that an end of the world brane should meet the boundary, should hit the boundary at that location. Okay, so it makes sense as a boundary problem. You specify the length of some interval. You say that the dilaton should have a particular value here, and the end of the world brane should encounter the boundary at both ends. And then you look for a classical solution that has that property. And if you look up here, you'll notice that this classical solution does have that property. So the black line has a length which we can fix, and the end of the world brane in blue here touches the black line at its two endpoints. Okay. So the way this is going to work is that the state where the end of the world brane is in a particular state I is going to be represented by an endpoint of this black line where an end of the world brane of type I encounters the boundary. So in particular, if the end of the world branes at the two sides are in the same state, then what we're computing here is a normalization factor, the inner product of two of these end of the world brane states, psi I with itself. I put a hat here to emphasize that these are unnormalized states. So this gravity computation here is computing the inner product of a state psi I with itself, where psi I means a state of the black hole system where an end of the world brane is in state I. Okay, so let's see what the gravity path integral tells us for the inner product of that state with itself. We're supposed to compute the path integral of JT gravity on this space here. And let's first just think about the topological term in the JT gravity action, the S naught times chi, where chi is the Euler characteristic. The Euler characteristic of this space here is 1 because it's topologically a disk. So that term in the action will be e to the s naught times chi versus e to the s naught. So the level of the topological term in the JT gravity action, this inner product psi I with itself is equal to e to the s naught. And in fact, for today, we're just going to simplify the JT gravity action by keeping only the topological term. We're going to make our lives easy and forget about the rest of the JT gravity action, the extrinsic curvature term, the bulk term. We're just going to focus on the dependence on the topological term. So in order to evaluate the action of gravity configurations, your job is really easy. You just need to remember that the Euler characteristic for a geometry with a topology of n disks is equal to n. So for one disk, it was 1, for 2 disks, it would be 2, and so on. So that means the configuration which has the topology of n disks will say that the JT gravity path integral gives the answer e to the n times s naught. So that's a simplification of the real answer, but it's already enough to see the basic point. And on Friday, we'll put back the rest of the JT gravity action and do a more precise job. So far we've discussed the inner product of the end of the world brane state with itself. Next in complexity, let's consider the boundary condition for the inner product of two different end of the world brane states, psi I and psi j. So these states psi I and psi j are states of the black hole where the end of the world brane has state I or j. And it makes sense to consider the inner product. So the boundary conditions to compute this inner product are similar to what we've been discussing so far. The difference is that the end of the world brane that we require to encounter the boundary at the two ends of this interval are in different states, I and j. So inner product psi I, psi j is given by a gravity problem with the boundary conditions shown on right. We take an interval of some fixed length and fixed value of the dilaton, and we require an end of the world brane to hit one end, end of the world brane of type I to hit one end, and an end of the world brane of type j to hit the other end. So what's the geometry that fills in these boundary conditions? Well, that's actually just the same geometry we've been discussing so far. The end of the world brane that starts here has to end somewhere. The only place it can end is at the other end of the interval. So the end of the world brane, shown in blue here, connects the two ends of the black interval together. And you see that the same end of the world brane propagates from one side to the other, which means that this quantity will only be non-zero if I is equal to j. So this inner product is actually proportional to Kronecker delta ij times the same factor e to the s naught that we had before. Why is there the e to the s naught there? It's because we have one disk, the topology of one disk. So we get e to the s naught. Okay, so we can use this result to compute the density matrix of the radiation. So sorry, I have to go back a little bit, but if you start with this state here and you compute the density matrix of the radiation, then you take a ket copy and a bra copy of this state and trace over the black hole system. And it's a simple calculation to show that the density matrix of the radiation that you get is given by this expression here. Okay, so let me explain a little bit what this expression looks like. So this part here is an operator in the R system. That's the actual density matrix. And this part here is just, this is a number. These are the inner products in the black hole system that determine the density matrix of the radiation. We're dividing by k because of the 1 over square root of k in the definition of the state. And we're dividing by e to the s naught because these psi hats are not normalized. So if we divide them by e to the s naught, then they become normalized states. So this is a properly normalized density matrix. And if you plug in this answer for psi I, psi j inner product, then the e to the s naught cancels the e to the s naught in the denominator. And we get a Kronecker delta ij, which sets the density matrix equal to this expression here. So in other words, we find a maximally mixed density matrix. And the entropy of that density matrix is log of k. As we discussed at the beginning, its purity is 1 over k. Okay, so now finally, we've got to the point where there's a problem. The problem is that if we make k really, really big, k is a parameter at our disposal. If we make k really, really big, then this entropy will be very large, larger than the black hole entropy. So we'll have this bag of gold problem that Ahmed explained. So in other words, our expectation is to get this answer, minimum of log k and S black hole. And it looks like we're just getting log k. And that's a problem if it happens that log k is bigger than S black hole. Okay. But something kind of interesting happens if we compute the purity directly. So we compute trace of rho squared directly. In the previous slide, what we did was we computed this inner product, and then we plugged it into the formula for the density matrix. Then we computed the purity of the density matrix. Normally, that's fine. That's a perfectly legal thing to do in quantum mechanics. But we could wonder whether it's okay in gravity. And to check it, let's compute the purity directly. So let's compute trace rho squared directly. So here I've written in a formula for trace of rho squared that you get by starting with the formula for the density matrix here and just computing trace of rho squared. Okay. So let's first write the boundary conditions that are associated to this quantity. So we have two copies of a psi I, psi j inner product. So look at the left here. We have two copies of the same boundary conditions that we've been discussing so far. We have this interval of some length, and at the two ends, we require an end-of-the-world brane of type I and j to encounter that interval. We have two copies of that boundary condition, and the most important aspect of this entire lecture is that there are two different ways of filling in these boundary conditions. There's an obvious one where we just take two copies of what we've been discussing so far, two of these topological disks, or there's one where we fill it in with a connected geometry. This is a wormhole because it connects together these two different boundaries. Black lines are boundaries, blue lines are end-of-the-world branes, and you can see that this geometry here connects together the two black boundaries. Okay, so let's see what we get from these two different contributions. So first, let's look at the first one. As you can see, the end-of-the-world branes connect together the I and j indices. So I will have to be equal to j in this computation. So we'll be summing over I and j with a Kronecker delta ij. Okay. And we're going to get a factor of e to the s naught from each of these two disks. The Euler characteristic of these two disks gives 2. So we'll get e to the 2 s naught times a sum over I and j of Kronecker delta ij. So a sum over two indices that are required to be the same just gives one factor of k. So we get k times e to the 2 s naught from this diagram. When we sum over I and j on this diagram, you'll notice that I is connected to I by the end-of-the-world brane, and j is connected to j. So we have two unconstrained sums, independent sums over I and j, which gives us a factor of k squared. This diagram here comes with a factor of k squared. But the Euler characteristic is only 1 because we have one topological disk. We had 2 on the left, we only have 1 on the right. So we get e to the s naught on the right times k squared. Okay, so let's take this formula here. This is the sum over I and j of the matrix element squared and plug it into our formula for trace rho squared. And to do so, we just take this thing and divide it by k squared e to the 2s naught. Just multiply by this factor here. And what does that give? Well, the e to the 2s naughts cancel in the first term, and we get one extra factor of k in the denominator. So we get 1 over k for the first term, and for the second term, we get 1 over e to the s naught. Okay, so that's the result of our little computation, and let's try to interpret it. So first of all, the purity of a maximally entangled state is 1 over k. That was a little computation we did at the start today. So 1 over k is the naive answer. What is this 1 over e to the s naught doing here? Well, one thing you can notice is that if k is really, really big, then the 1 over e to the s naught term will dominate. So we'll find that the purity is roughly the maximum of 1 over k, or 1 over e to the s naught. And that should remind you of the island formula. So that when k is very large, then the answer is no longer the entropy of a maximally entangled state. It's instead something that depends on S naught, the entropy of the black hole. Okay, there's some puzzle here that, well, in the interest of time, maybe I'll skip this puzzle. And let me return to the main story. So, so far we computed the purity, trace of rho squared. And we found that when we computed it directly in gravity, we got an interesting answer. There were 2 different terms. We would like to do the analog of that computation for the von Neumann entropy. So the von Neumann entropy is harder to compute than in quantum mechanics, it's often harder to compute than the Renyi entropy. That's because it involves this rho times log of rho. But that rho times log of rho can be realized as a limit as n goes to 1 of log of trace of rho to the n. So this is a formula called the replica trick for computing the von Neumann entropy. So let's try to compute this quantity on the right-hand side. Let's try to compute a trace of rho to the n. So I'm going to draw for you here the boundary conditions for computing trace of rho to the n. We have n different segments of boundary, 1 for each of the copies of rho. And they have end of the world branes that are supposed to intersect the boundary at the start of the segment and at the end of the segment. The boundary conditions are such that the end of the world brane flavor at the end of one segment has to be equal to the end of the world brane flavor at the beginning of the next segment. So it forms one big circle like this. That's because we're computing the trace of a product of things. So if we go back a second, you can see that the boundary conditions here for trace rho squared were a special case of that. The end of the world brane flavor at the beginning of this segment was equal to the end of the world brane flavor at the end of that segment. Okay, and the same is true for trace rho to the n. We just have n of these boundary segments. And there's a lot of different ways of filling in this kind of configuration with two-dimensional geometry. Here I've shown 2 sort of extreme ways of filling them in. One extreme way is each boundary is completely disconnected from the others. So the two-dimensional gravity region is shown in gray, and we just have n separate topological disks attached to each of the n boundary regions. The other extreme way would be one fully connected geometry that connects together all of the different boundaries, all n of the different boundaries. So what we would like to do is compute both of these things and then apply the replica trick formula. Take the limit as n goes to 1 to compute the von Neumann entropy. So let's try to get a sense for what the answer looks like. So first of all, we need to, so here's the answer for trace rho to the n. Let's try to understand it. First, we have a factor up front. That's a normalization factor for each of the n copies of rho. 1 over k times e to the s naught to the power n, 1 for each of the copies of rho. So this is a relatively boring factor, just an overall normalization. Then in brackets here, we have the different ways that geometry can fill in these boundary conditions. The one on the left corresponds to the diagram at left here, and the one on the right corresponds to the diagram at right here. So let's try to understand these factors. First of all, why is there one factor of k in this expression? Well, you can see that there's one dotted index loop in this diagram. The dotted line represents the I and j indices. And because the end of the world branes are in this configuration here, connecting the beginning and the end of each segment together. And because the end of one segment has the same value as the beginning of the next segment, there's just one value of the index I of the end of the world brane, which is common to all of these diagrams. So there's one gigantic Kronecker delta that sets all of the end of the world brane indices to be the same. And then when we sum over the indices, we just get one factor of k. The other factor is this the topological contribution of the topological term in the JT gravity action. We have n separate disks here. So we get a factor e to the n times s naught. Okay, and I'll leave you to figure out this second one. It's similar logic, k to the n e to the s naught. And now we can just do a very simple piece of math, plug this formula into the replica trick formula. And you find that the first term contributes log k, and the second term contributes s naught. So I went a little bit quickly over this because I'm out of time, but I encourage you to take a look at this slide afterwards and make sure that you understand, first of all, why this is the right answer for the term on the right here, and second, how substituting these into the replica trick formula gives these two answers, log k and s naught, for these two terms. Okay, so that's the beginning of the island formula, a term involving log k and a term involving s naught. And we'll finish the calculation next time. So let me stop here.
Okay, let's unmute and thank Douglas. Okay, so there are a couple of questions. So Gabriel is asking, are there some smooth conditions for the end of the world brane? Why the vertex doesn't contribute to the Euler characteristic?
Okay, so yeah, it depends how you do the calculation. So the Euler characteristic of something with the topology of a disk, even if the boundary has corners in it, the Euler characteristic of that thing is still 1. So you're right that in computing the Euler characteristic, you have to be careful about corners. But what that means is that if we were to compute this Euler characteristic by doing an integral of the curvature in the bulk and the extrinsic curvature along the boundary, then we would have to remember to include a contribution from the corners. But that's not how we're doing the calculation. We're doing the calculation by just remembering that the Euler characteristic of anything with the topology of a disk is 1. And so then we don't have to decompose it into a contribution from the corners and a contribution from everything else.
Okay, then Muhammad is asking, could the end of the world brane be an RT surface? If yes, is it physically meaningful?
Well, an RT surface is some location in the bulk, and it's codimension 2. The end of the world brane is codimension 1. It's like an end of space-time. So you could imagine a situation where the RT surface is close to the end of the world brane, but they're not the same thing.
Okay, then Himanshu is asking, is the replica wormhole similar to the wormhole that appears in the computation of spectral form factor?
Yeah, it's similar in the sense that it connects together two boundaries, and it's similar in some respects and different in others. One way it's different is that although these two boundaries are geometrically separated from each other, they're kind of connected here by the sum over I. You notice that the end of the world brane value at this end is the same as the end of the world brane value at that end. And so that sum over I is like a type of correlation between the two boundaries, which is not present in the spectral form factor. So in some ways they're similar, but in other ways they're a little bit different.
Okay, and we have a few raised hands. So Berat, can you go ahead, please?
Okay, so I have 2 questions. Can you go back to that Lorentzian picture that you had and the world brane behind the horizon?
Is this what you wanted?
Yes. So I'm most probably confusing myself, but I was just wondering, I believe you said it's not important where to put the end of the world brain. So imagine a case that I put it where it almost touches the bifurcated surface.
Okay.
Then it seems that there is no island region, right? In that case.
Oh, I see. Well, in that case, the island region would be small in space-time, but it would still include the part of the end of the world brain. And that's all that's important, is that it includes part of the end of the world brain, let's say at t = 0. So I think what you have in mind, maybe I can try to draw. You have in mind a case where the end of the world brain follows some trajectory like that there, right?
Yeah, exactly.
Okay, and now if we look at this, it looks like the island region is tiny, very small. And that's true, but it does include part of the end of the world brain at t = 0. And that's enough to capture the internal state of the end of the world brain. If you know what the state is at t = 0, then you know what its internal state is. And that's all that's important in this computation of the entropy.
I see. Also, is it possible that you say a few words about the comment that Kyriakos made in the beginning about the the case being overcomplete? What is the origin of that?
Okay, good. So from the perspective of gravity, these states with an end of the world brain are just some states of the black hole. As Kyriakos was saying, there's some kind of time-dependent states of the black hole where there's an end of the world brain behind the horizon. And when we make k large, we have a very large number of these different states. And if k is much bigger than e to the entropy, then those states have to be linearly dependent because the Hilbert space is just not big enough to fit them all. So that means they have to be overcomplete. And actually, we can see that in the computations that we did. So when we did the first computation, psi I, psi j, the answer we got was proportional to Kronecker delta ij. So it looks like these states are orthogonal. Okay, but that can't be because we can have as many of them as we want. And if we have too many of them, they can't all be orthogonal. That's like what we learn in freshman linear algebra. If you have too many states, too many vectors in a finite dimensional Hilbert space, they can't all be orthogonal. And the signature of that was when we computed the square of this inner product. We found a contribution, this first term, that's only non-zero if I is equal to j, but we found some other term that was non-zero even if I was different from j. So this wormhole contribution is telling you that these states psi I and psi j are not quite orthogonal. And that's the origin of the overcompleteness that Kyriakos was expecting.
Thank you.
Okay, John, can you go ahead, please?
Oh yeah, so I have a question, but from the lecture of yesterday. I don't know if I can do it now or maybe I can do it another day. I'm curious about something. Maybe I can do it later. I don't mind.
Well, maybe you could save your question to the end or ask it on Slack if we don't have time.
Yeah, I can do it or for the end, whatever on Slack. Yes, thank you.
Okay, let me just quickly read two more questions and then we stop because we have to take a break. So Farad is asking, at the end, does the other terms which connects not all of them, but one of the boundaries or two, etc., getting neglected because of their very low contributions?
Oh,
I guess the question is, yeah, about these intermediate terms that.
Oh, good. So, yeah, this is an interesting question. It turns out, oh dear, I've screwed up my Zoom. Okay, there we go. It turns out that most of the time, for most values of k, you basically have to care about only the extreme case, only this case here or that case there. But if log k is close to S0, then you start to care about intermediate things. And so we'll see tomorrow how the transition between log k and S0 can be smoothed out by including things with an intermediate amount of connection, as you were expecting.
Okay, and the final question by Rita. Is the replica wormhole in Euclidean signature a manifestation of the island in Lorentzian signature? And if so, why?
Yeah. So the island, okay, so the island rule is some rule for computing entropies in gravity. And it was sort of a guess. And if you try to derive that rule from the gravity path integral, then it turns out that you can derive it. So the guess or the conjecture of the island formula is correct, but the derivation of that thing involves replica wormholes. So the simplest example of that is this wormhole here. And so yeah, the island formula is ultimately justified by the fact that you can include these replica wormholes.
Okay, so if there are more questions, you can ask them tomorrow or during the tutorial or on Slack. So let's thank Douglas again for the great lecture.
See you guys on Friday.
Great, and we will meet again in about 10 minutes from now with a tutorial on mock modularity.